So today we're going to discuss a new, unusual, unexplained radio signal somewhere out there. But let's just get it out of the way. Not aliens. Pretty sure it's not aliens. Like 99.9% sure it's not aliens. So if you came here for aliens, don't leave yet, stay for science. Because today we're going to discuss one of the more bizarre radio discoveries in the last few years that the scientists have actually never seen before. And once again, it was discovered completely by accident. And so, hello wonderful person, this is Anton. Let's discuss this new discovery of an unusual radio transient discovered extremely recently, talk about what it probably is and what it most likely represents, and why this is important for astronomers. But I guess first, let's get a few definitions out of the way. So this is called a radio transient. In essence, an unusual burst of radio waves coming from somewhere out there in the universe that in some cases only erupts once or sometimes can flicker or be even predictable. And when it's predictable like what you see right here, it's something we refer to as a pulsar. And today we know quite a lot about pulsars. Here's for example the famous Vela pulsar, visible in the X-rays as seen by the Chandra Observatory. And so we know that in many cases, as the neutron stars spin and as they emit their jets, they tend to actually produce a lot of different emissions depending on what they interact with or where the jets are pointed. And so in many cases, repeated radio transients are essentially almost always neutron stars. But in pretty much most cases, these neutron stars spin pretty fast. And that's because they're really small in size and because of the conservation of angular momentum. As a large star becomes smaller and smaller, it starts to spin faster and faster. And since neutron stars are only a few kilometers across, they basically end up spinning at ridiculous speeds. Many of them spin hundreds of times per second, which means that radio pulsations come to us several hundred times per second as well. These are usually called millisecond pulsars. But in one of the recent studies, the scientists discovered something we've really never seen before. Because despite being a radio transient, it seems to have a very strange cycle. A cycle that seems to be at least 54 minutes long, but also seems to change quite dramatically over time. Sometimes it seems to emit a lot of really long, bright flashes, sometimes fast and weak flashes, and sometimes it does absolutely nothing. Which means that the researchers just discovered the strangest radio transient we've seen in a very long time. Something that you're going to see appearing in this image right here, and something that nobody right now can explain. But it's most likely, at least according to the scientists, some kind of a neutron star. Although out of approximately 3,000 neutron stars discovered so far, this by far is the strangest yet. Because if it is a neutron star, it seems to be spinning super slowly. Instead of spinning like hundreds of times per second, it basically takes 54 minutes to spin just once. And if that's the case, it actually doesn't really make a lot of sense. And so what exactly is this? Well, first of all, the name. It's currently known as ASCAP J1935 plus 2148. And the numbers here are important because they actually show the location. And the location is extremely close to another source, SGR 1935 plus 2154. And if you've never heard of this, check out one of the videos in the description because this is basically one of the biggest discoveries in radio astronomy. It's a fast radio burst that came from right here in the Milky Way from an extremely famous Magnetar. And so that's basically how this other source was discovered. The researchers were actually trying to discover even more fast radio bursts coming from SGR 1935, but instead, completely by accident, they discovered another source very close. And here it was just blinking every 54 minutes, producing very slow flashes, but flashes with what's known as circularly polarized radio waves, implying powerful magnetic fields, which is probably why it's not really aliens. But then by using additional observations from South African Meerkat telescope that's even more sensitive, they were essentially able to confirm that this seems to be a neutron star after all, but just an extremely weird one we've never seen before. And it also seems to possess at least 3 different modes, sometimes every 54 minutes, it produces a very bright, linearly polarized pulses that last for about 10 to maybe 50 seconds. This is kind of what you see in this time lapse. But sometimes it produces extremely quick pulses that are circularly polarized, here only lasting 300 milliseconds. Yet sometimes it does nothing at all. And that basically suggests that, okay, maybe there is something orbiting this neutron star and something disturbing it, producing different magnetic effects. Or maybe it's in the middle of some kind of a really large cloud, such as a pulsar nebula, that's able to change its effects over time. So basically here there is a lot of activity around this object. Or maybe this is not a neutron star and instead some kind of a magnetized white dwarf. Technically, a white dwarf could be spinning so slow and could actually produce some radio emissions. But the problem is that white dwarfs normally don't produce radio emissions that are so powerful. This object is believed to be at least 16,000 light-years away from us, and no white dwarf has ever been seen producing such powerful radio emissions. And so instead it's actually believed to be some kind of a slow-spinning neutron star with maybe a white dwarf or even some kind of a different star orbiting around it, which could explain why the light coming from here seems to be polarized differently, or sometimes nothing appears at all. And so at the moment, a slow-spinning neutron star is still the best explanation. And if that's the case, it basically shows us an extremely important part of the life of a typical pulsar. In essence, it shows us what happens to pulsars right before they stop being pulsars, right before they die. It's actually believed that over time pulsars slow down, and at some point, once they spin slow enough, they switch from being pulsars to being just regular neutron stars. And so maybe this is actually what we're observing here. Maybe out of 3,000 neutron stars, this one is the first discovered that shows us a transition from a pulsar to a dormant neutron star. But these are just speculations for now. Way more research is needed and a lot more observations are required before all of this can be confirmed. Either way though, this discovery is super exciting for a lot of scientists interested in neutron stars, pulsars, fast radio bursts, or radio transients in general. Because by discovering such a unique, unusual object, this research will definitely lead to a lot of exciting discoveries in the next few years. Although interestingly, in this case, since radio researchers usually don't look for such long signals, it's actually surprising that this was even discovered. One of the reasons it was even seen is because the Australian ASCAP telescope that was able to find this usually sees things in the much wider field of view and is also able to see things in a very different time frame. But I guess for the most part, the researchers basically just got super lucky. And so even though they were looking for fast radio bursts, instead they discovered literally the slowest radio burst ever. A new exotic radio phenomenon that currently does not have a very good explanation. But not aliens, probably. Although as a side note, this is actually not the only such object known to us. At least 3 similar phenomena have been discovered before, which are now referred to as long-period radio transients. Objects that emit very polarized light, lasting for tens of seconds, or even several minutes, separated by relatively long periods in between. And because this object was also able to produce relatively fast radio bursts, here the scientists don't think it can be anything but a neutron star. Based on the emissions in milliseconds, this basically constrains the total size of this object, so it can only be maximum of a few kilometers across. Or basically because of the speed of light, the maximum size of this object is just a few tens of kilometers. While at the same time, because the scientists observed several pulses, and those pulses changed with time, it actually suggests some kind of a change in the region around this object, implying physical changes, possibly from some kind of a plasma or some kind of a gas surrounding this object. And so basically here, in order to learn more, and in order to find out exactly what this is, scientists would have to observe this for at least a few more months. And so at least for now, we're going to assume that it's most likely a neutron star, or maybe some kind of a really exotic, unusual object we've only seen before 3 times. Either way though, a super exciting discovery and yet another anomaly or another mystery to solve in the next few years, and something else we're going to be discussing in some of the future videos once someone figures out what's actually happening here. In the last few months, several telescopes released some of the most incredible images of very famous nebula. Nebula like the one you see right here, Cassiopeia A, and this one, the famous Crab Nebula. With these new images showing us a lot of new things we've never seen before, but also some things that are kind of mind-blowing. For example, we actually now have a time-lapse lasting for approximately 20 years, showing us how all of this changed over time and how some of these nebula transformed, even though from a distance they do appear pretty still. But I guess more importantly, the three objects we're discussing today are what's known as the supernova remnants, and all three were formed in very similar conditions, but at extremely different time frames. One of them is very young, one of them is somewhat in the middle, and one is really old. But all three are super famous and very well known, and though we've discussed them before, we now get these incredible images that show them in a completely different light. And so, hello wonderful person, this is Anton. Today we're going to discuss the Crab Nebula, the Vela Nebula, and the Cassiopeia A. Basically some of the most well-known objects in the entire galaxy, and the objects that, despite being somewhat similar, are actually very different, with the only thing that's basically common being their origin. They're all the result of a relatively similar star going supernova, and here we're talking about a star that's about 8 to maybe 20 times the mass of the Sun, and a star that then left behind some kind of a remnant in the middle, with some of these images even showing us this remnant. For example, here's one inside the Crab Nebula. But I guess more importantly, because these images were taken by different telescopes, we actually get to see completely different things in separate images. But I think one of the most impressive images, or technically videos, is this. The time-lapse taken by the Chandra telescope, showing us the changes in time, with this time-lapse lasting for approximately 2 decades, visible in the X-rays, and basically around the central structure, also referred to as the Pulsar Wind Nebula, or basically the nebula inside the nebula, which is very often formed by pulsars interacting with the gas around them. And so I guess let's start with Crab Nebula, probably one of the most famous objects in the galaxy, discovered by William Parsons back in the 19th century, who for some reason in his telescope believed that it kind of resembled a crab. And so he basically referred to this as the Crab Nebula. And here's one of the older images from 2005 taken by the Hubble telescope. Now, I don't really see the crab, but it definitely looks impressive. And today we know exactly when this object formed based on the observations from various ancient astronomers. It seems to have appeared in the night skies on July 4th of 1054, almost 1,000 years ago. And even though the nebula is about 6,500 light years away from us, the light from this nebula was bright enough to be seen in bright daylight, but it basically resembled a kind of a new star, because it was obviously still far away. Here's roughly what all of this looks like if you were to combine all of the frequencies of light into one image. And so during these 1,000 years, the structure has expanded to be about 10 light years across, and is actually still bright enough that it can technically be seen even by using binoculars. And though the images from Hubble only showed us visible light, the new images by James Webb now revealed infrared. And this actually looks entirely different. As a matter of fact, this image taken a few months ago does not show us the shock waves and the hot gas visible by Hubble, but instead shows us cold dust, especially carbon molecules, various types of silicates, with this very strange ghostly glow, or I guess milky glow, formed by various trapped electrons moving super fast around the nebula because of super powerful magnetic fields around the pulsar. And that's really the important part here. Right in the center, you actually do get to see the pulsar. And though it might be difficult to see at first, it does become a lot easier to see in the X-rays. And so because we see a pulsar, we can only assume that the original star, the Progenitor star, was probably up to 20 solar masses. But that actually creates a bit of a problem. There are no 20 solar masses of gas in here. The neutron star is just under 2 solar masses, the nebula is about 5 solar masses, and so there's about 10 solar masses of stuff missing. It's assumed that maybe it's just invisible to us because it's some other dust particles or something else, but it's basically one of the modern mysteries. Where's the rest of the stuff? Nevertheless, James Webb definitely revealed a lot of details. For example, all of this reddish-orange stuff is ionized sulfur, whereas the blue stuff is ionized iron, with a lot of other dust, including various carbon molecules, appearing as greenish yellow. But it's of course the Pulsar nebula that produces all of these unusual tendril shapes, making it appear as some kind of an unusual space creature. And so basically everything here is sort of formed by this. This tiny dot in the middle is the reason for all of these unusual shapes. But here all of this becomes even more intriguing once you start comparing this to similar objects formed much earlier or much later. Let's actually take a look at one of the oldest similar objects in the entire galaxy, the Vela pulsar. Interestingly, the pulsar that also produces an extremely similar formation, once again seen by Chandra. But Vela pulsar is also one of the most powerful objects in the entire galaxy. It's even able to produce gamma rays, as seen in the observations right here. But it also appears much brighter because of the distance. It's only 800 light years away from us, and so it obviously appears a little bit lighter. And so here, very recent observations by the Dark Energy Survey, using some of the most powerful cameras we have on the planet, the researchers revealed some of the most detailed pictures of this whole region. Here's a very slow zoom showing us where the supernova remnant is located. And interestingly, this is also one of the oldest such objects in the galaxy. It was very likely produced 11 to 12,000 years ago, making this object at least 10 times older than the Crab pulsar, yet surprisingly, it's much brighter and much more powerful. As a matter of fact, this is believed to be the most powerful pulsar in the entire galaxy. It spins approximately 11 times per second, and the remnants from the explosion are still traveling really fast, approximately 1200 km per second away from the center. And so as a result, it formed this huge structure, approximately 100 light years across, or once again about 10 times larger than the Crab Nebula, and in essence it shows us the kind of an end process for most of these supernova remnants, as all of this material blown away by the supernova disperses into interstellar space, mixing with all of the gas that's eventually going to become new stars and new planets. But what we're seeing here are, of course, the shockwave collisions with a lot of interstellar gas, which then forms all sorts of filaments visible in this image. Here's the annotated version showing us the biggest shockwave, but also the Vela pulsar barely visible right there. With this image also showing us a wide variety of different elements, mostly ionized, and basically produced by the supernova. Here we see calcium, carbon, copper, magnesium, nickel, oxygen, silicon, and even things like krypton and germanium. All of them detected in that one single image. And so in essence, this is what most supernova usually end up as. The shockwave eventually mixes with all of the gas in the galaxy, leaving behind some kind of a lonely remnant like the Vela pulsar that's surprisingly still going strong even after 12,000 years. And so here it's, I guess, worth comparing how the gas transitioned in these thousands of years from what we saw in the Crab Nebula, where things are still much more compact and are still controlled by the Pulsar Nebula itself, compared to what we see right here, where the shockwave is now mostly interacting with the interstellar gas, and the pulsar no longer has any effects. But naturally, it's also worth taking a look at something even younger, and it just so happens that James Webb took pictures of that as well, with Chandra even adding its own images producing time-lapses. This is the famous Cassiopeia A, and this beautiful X-ray time-lapse in essence shows us how this changed in approximately 2 decades. And Cassiopeia A is essentially the most recent addition to the Milky Way galaxy, very likely formed by a somewhat similar star to the one that formed Vela and Crab, but in this case back in 1670s. So approximately 350 years ago. And though this object is about 11,000 light years away from us, it's one of the most well-known and one of the most studied such objects, just because this shows us basically the beginning of the supernova remnant. But surprisingly, unlike Crab and unlike Vela, there is no pulsar. Researchers believe there is a neutron star here, but for some reason it never became a pulsar, or maybe never became yet. So this is actually one of the mysteries here. Why is this not a pulsar, whereas the much older supernova remnants all have a pulsar in the center? In case you're wondering, the main difference between a neutron star and a pulsar is that the pulsar emits pulsations, allowing us to see them from really far away. Neutron stars, on the other hand, are believed to be basically similar but just quiet and with possibly much milder effects. And this object is also much smaller. It's a lot more compact, even though it does possess these similar tendrils, with this explosion potentially even being much more powerful, because it's actually relatively similar in size to the Crab Nebula, which is older, with the material here moving really fast, up to 14,000 km per second, while also forming a lot of filaments basically resembling broken glass, possibly highlighting how extremely powerful all of this was. With these new images also showing us a few unexpected features, like the strange blob in the bottom right. The researchers are now calling this Baby Cassiopeia A, and though it might look like part of the nebula, it's actually not. This is just a reflection, or technically a light echo, produced by the light from the supernova hitting a very distant clump of dust that was probably there even before. But more importantly, once again the images from the James Webb reveal a lot of different elements. Sulfur, oxygen, argon, which is what all of this is made from. And once again, a lot of this milky stuff, or this white stuff, this is electrons moving at very high velocities as a result of the magnetic field. Something that looks even more incredible if you look at this from a distance, with obviously different colors being produced by different elements. But in that sense, it's not so different from the previous supernova remnants, because the elements seem to be relatively similar, which basically shows us how these objects evolve over thousands of years. With these beautiful detailed pictures now taking us a little bit closer in helping us understand how these objects evolve. But it's really these X-ray time lapses that, to me at least, seem to be absolutely mind-blowing. One showing us how the Pulsar wind nebulae changes over time, highlighting the extreme power of these very dense objects, with the other one showing us how the Cassiopeia A changed as well, visibly expanding over time even though it's already 10 light years across, which once again highlights how powerful this explosion was and how even today the material here moves really fast, 6 to 14,000 km per second. But because these are relatively recent images and we don't actually have any studies about them yet, chances are that in the next few months we'll be hearing more about the actual discoveries and possibly even more explanations on supernova remnants and how they transform galaxies over time. Because surprisingly, even though all three of these objects were formed by similar phenomena, they don't really look same at all. And that's probably because of the age difference. And so we'll definitely come back and talk more about this once there are some updates or something else is discovered about these objects in some of the future studies. It's now been approximately 14 years since the original discovery of FRBs, or fast radio bursts. Very strange, unexplained radio emissions, very powerful emissions, that at first scientists thought might actually come from planet Earth, from things like maybe satellites or even microwaves. But as the time went on, and as more and more have been detected, along with some really thorough observations, scientists realized these are actually coming from very distant galaxies and seem to be coming from pretty much everywhere, suggesting that these are powerful events with a single burst equivalent to the amount of energy our Sun produces in approximately 1 year. But a single signal here is always shorter than 1 second, which is why they're known as fast radio bursts. And because they're so short, and because these are radio signals coming from really far away, it's been suggested that they're probably formed by something relatively small. Basically, for the light to travel in such a short time, this has to be less than 300 kilometers in size. So possibly some kind of a black hole, maybe a neutron star. But even after 14 years of research, there is still no clear explanation, even though one of these events has been detected right here in the Milky Way galaxy. And so, hello wonderful person, this is Anton. Today we're going to discuss some of the recent discoveries in regards to FRBs, and actually 2 potential explanations to how they form somewhere out there. And both of these new studies decided to focus on 2 most famous FRBs, the closest one to us, and the one that's known to repeat quite a lot. And this is based on a very famous neutron star, specifically a very famous magnetar, known as SGR 1935 plus 2154. Here's roughly what this location looks like in radio light, and here's the same observations done with X-ray telescopes. And so a few years back, as we've discussed in one of the videos right there in the description, completely by accident, researchers studying this magnetar discovered that it seemed to have produced a fast radio burst. And not just 1 or 2, it produced quite a few. And during this time, this object was observed by X-ray telescopes before and after the event. obviously with the main purpose of understanding how all of this forms. And so in October of 2022, and even several times before that, it produced a few fast radio bursts captured by several telescopes such as NASA's NICER, located on the International Space Station. And interestingly, one of the main discoveries in this case was the fact that something happened to this magnetar before and after this FRB. In essence, it experienced what's known as a glitch. And this is a term used in astronomy to talk about neutron stars that for some reason sometimes accelerate just a little bit when it comes to their rotation. And so in this case, this magnetar suddenly started spinning just a little bit faster and did this twice. And in between these two glitches, that's when this FRB seems to have happened. And I guess here it's kind of important to understand exactly what we're talking about. We're talking about something that has a mass of the Sun, technically even more, but is smaller than the city of New York. And so this extremely dense, really massive object, spinning really fast, if it accelerates just a little bit in its rotation, whatever happened here must have involved a tremendous amount of energy. And this particular magnetar spins 3.2 times per second with its surface velocity of approximately 11,000 km per hour, or approximately 3 km per second. But suddenly, within just a few minutes, it changed that velocity by just a little bit and did so twice. And whatever caused this must have been super powerful. But in between these glitches, what surprised the scientists behind this recent study is that this magnetar also slowed down in approximately 9 hours. Or basically it slowed down much faster than ever observed around any neutron star. It's not entirely clear why, but because of this extremely fast decrease in rotation speed, it's believed it resulted in the release of these very fast radio bursts. Basically, it had to somehow shed all of this energy, and this was done through radio burst emissions. Now, normally, in a typical magnetar, when it suddenly accelerates, or when it experiences this glitch, it usually takes weeks or even months to get back to its normal speed. Here, though, it only took 9 hours. And though obviously this was a very surprising discovery and currently does not have a very specific explanation, it shows us that we still know so little about magnetars and they're still full of mysteries. These are obviously some of the most powerful objects in the entire universe, representing some of the most extreme neutron stars with a ridiculously powerful magnetic field. Fun fact, or I guess a scary fact, if you come really close to one of these objects, the power of the magnetic field is actually going to disturb a lot of chemistry in your body, and even the atoms inside your body are going to become ripped apart by ridiculously powerful magnetic fields. So yeah, death by magnetar is maybe not the way to go. But I guess back to FRBs. So what the scientists now learned about this is that it seems to be the result of whatever is happening inside magnetar, and specifically the very extreme conditions formed by quantum mechanics when things become ridiculously hot, very pressurized, and quantum in nature. Today, based on what we know about quantum mechanics and experiments with extreme matter, scientists believe that a typical neutron star consists of at least two states of matter. We have a kind of a solid surface that's basically crushed by the gravity so much that even a single mountain here cannot be taller than just 1 millimeter. And then we have a kind of a quantum superfluid inside that potentially resembles a typical fluid in the way it interacts with everything else. But because these objects spin, here the researchers explain some of these effects as essentially, well, I guess a fishbowl spinning around. Because of the sloshing of the liquid inside this object, sometimes the liquid can spin just a little bit faster than the surface, meaning that the surface, the crust, or the fishbowl's glass, has to somehow catch up. And that's when the glitch occurs, with this extra energy released in the process. And so basically the internal liquid and the external surface, solid surface, do not really spin at the same velocity at all times. But when they become out of sync, something has to happen in order to release the energy from the inside by delivering this to the crust, which might occasionally even crack the surface, to some extent resembling a kind of a ridiculously powerful volcanic eruption. And so by losing this mass very suddenly, it causes the object to spin just a little bit slower, thus explaining this rapid deceleration, but also possibly the sudden release of fast radio bursts. At least that's the explanation we have for now. It's still super preliminary and there's no actual evidence, just the theory behind this, but naturally by studying a lot of superfluids and interaction of superfluids with a lot of other extreme matter, we might be able to come to a conclusion of how this works. And naturally one day, this could potentially be used in practical way right here on planet Earth. How? I don't know. Somehow. I mean, we've discovered ways to use other stuff, so this might also get used somehow. My guess is some kind of a super cool scanner, like a super advanced MRI or something. I don't know. Anyway, moving on. So that's our first observation from the closest FRB to us. But then we have the most famous one, or I guess the one that's repeated the most. This is a really famous FRB detected in 2012 known as FRB 1211-012, and it became the first ever known repeated FRB. FRB that basically happened many times. It's already produced over 1,000 bursts, suggesting that whatever is happening here is happening over and over again. And in the last few years, scientists even identified the small dwarf galaxy where it's probably coming from. It seems to be at a distance of about 3 billion light years away from us. So yeah, despite the distance, we still see it really well. And so in this recent study, the researchers decided to analyze approximately 1,100 bursts from this FRB in order to discover some kind of a pattern to then try to explain what's going on here. And though at first it all seemed kind of hectic and potentially unpredictable, here by combining the results in certain ways, they were able to discover two separate periodic patterns. One seemed to repeat every 157 days, and one every 4.6 days. Basically suggesting that maybe something was actually orbiting with this FRB, thus producing these unusual observations. Although I guess a bit of a caution here. A bit of a follow-up from some other scientists suggested that maybe here the analysis conducted found patterns that might not really exist. So all of this is still super preliminary. But nevertheless, here we go. So what's the explanation? Well, as you can imagine, they suggest two separate objects. First, there seems to be some kind of a star with a 157-day orbit that once in a while disturbs the neutron star, potentially causing these glitches, and thus causing the release of powerful radio energy. That by itself is not super surprising. But it's that second result that is surprising. Here they actually propose that this object might have a planet orbiting every 4.6 days. And it's that planet that's causing the second signal. A planet that orbits at about 5% the distance of Earth to the Sun, and a planet that's potentially bombarded with a ridiculous amount of super powerful radiation. Here we're talking about gamma rays, X-rays, you name it, it has it. With scientists even suggesting that if this planet exists, it's probably supercharged with a lot of these particles, and possibly is always filled with some kind of a lightning or some other unusual effects. Likewise, if confirmed, this would also be one of the most distant planets ever discovered, basically at a distance of about 3 billion light years. But the question is, does this actually make any sense? Well, it kinda does, and for reasons that you see right here. This image was produced in regards to a different discovery. What you're looking at right here is a planet, a known planet, around a neutron star. As a matter of fact, these three planets are the first planets to be ever discovered in the entire galaxy back in 1992. Today they're known as Pulsar planets, but in a nutshell, because of slight deviations of pulsations from this neutron star, back in 1992 and 1994, Polish astronomers discovered that there are three separate planets here, and they all seem to be terrestrial, potentially resembling something like this. And more planets like this have been discovered in the last few years, but this one was obviously the first. You can learn about this whole system in one of the older videos, somewhere in the description. But the reason I'm showing you this is basically because, one, we know neutron star planets definitely exist, and so there's actually a slight chance that this is exactly what's causing the unusual radio emissions from this neutron star as well. But I guess two is that we can technically use this system to possibly see if we can detect similar emissions, or basically similar fast radio bursts, in order to basically test this hypothesis. Now right now nothing like this has been done, and as far as I know this system has not been studied for a very long time, but I think it's maybe a good time to take a look at it once again. It's roughly around 2300 light years away from us, and here this is not a magnetar, it is actually a pulsar, spinning 161 times per second. And so I guess technically, because this is not a magnetar, we might not see exactly the same emissions, but we might see something similar. And also interestingly, as far as we know, this particular pulsar was actually a result of a collision between two different white dwarfs, which is why it's spinning so fast. And so this whole system has a very intriguing and somewhat unusual origins. But more importantly, it might help us solve the mystery of the FRBs, or potentially help us discover even more mysteries, I guess. But anyway, the whole point I'm trying to make is that it's about time someone took a look at these particular planets once again, especially using some of the most modern telescopes. Let's discuss another unusual discovery that currently has no explanation. A discovery made inside this very beautiful and somewhat dense cluster known as NGC 1851, a relatively famous globular cluster located approximately 54,000 light-years away from the galactic center. In other words, it's not exactly inside our galaxy, but it does belong to the Milky Way. A cluster that's actually known for one of the highest densities of stars right in its center. But it seems to contain stars with the average age of about 9.2 billion years old, basically suggesting that this is a relatively ancient object that existed around the Milky Way, possibly from some of the earliest times when the galaxy was still forming. And it also contains a kind of a tail, very likely the leftovers from the ancient dwarf galaxy to which this cluster belonged. One of the studies in the description describes this unusual tail in more detail. But just like with other clusters, here scientists have also discovered pulsars, fast-spinning neutron stars that project two jets pulsating at regular intervals. Now, because this cluster is so far away from anything else, and because it contains such a dense environment of stars and a lot of other objects, it's usually relatively easy to study this, simply because any detection from this region usually means it's coming from the cluster. And so, completely by accident, extremely recently, the researchers using the Meerkat telescope in South Africa discovered something else inside the cluster, another pulsar. Okay, that by itself is not unusual, but what is unusual are the measurements coming from the pulsar. Normally, pulsars are known for their extreme periodicity, and they're actually so accurate sometimes that researchers even proposed using them as something that's even more accurate than the atomic clock. And since their pulsations are so predictable, any kind of a deviation means that something around the pulsar is probably causing it to wobble or change just a little bit. This technique is known as the pulsar timing array, and it's actually used to study quite a lot of different phenomena. One of the previous videos in the description describes using several pulsars in the Milky Way to discover something incredible about the universe. The universe seems to be vibrating. But here they discovered something else around this pulsar. Pulsar known as PSR J0514-4002E. E because this is not the first pulsar, with other ones having different letters. And this pulsar spins really fast, 170 times per second. And so any kind of a deviation becomes very apparent very quickly. And so by listening to radio frequencies coming from this pulsar and by looking at anomalies, they discovered a tiny wobble, or tiny deviations from the expected pattern. And that actually allowed the scientists to calculate a lot of parameters. First of all, the exact distance, the mass of the pulsar, the mass of the entire system, and if anything else is orbiting the pulsar. But also a system that seems to have tiny variations every 7.44 days. And that basically implied that there is a partner and a main neutron star, which basically suggested that this is a binary system. A system with a total mass of approximately 3.9 solar masses, a somewhat unusual mass. But because here they were able to calculate the mass of the neutron star directly, they were able to subtract the mass of the neutron star from the total mass, with the conclusion being that the second object seems to be kind of unusual and somewhat mysterious. Way too massive to be a white dwarf, yet clearly a separate object. A massive compact object with a total mass of possibly 2.6 to 2.8 solar masses. But not a star. It's too dim, it's invisible in most frequencies. And that leaves us with maybe two options. Another neutron star or a black hole. But both options in this case are difficult to explain because of the mass. To date, the most massive neutron star ever found was this one right here. Actually, another pulsar, PSR J0952-0607. It's just under 2.4 solar masses. And it's also spinning even faster, 707 times per second. But even at this mass, it's almost impossible to explain how it formed. This mass is essentially almost beyond the physical limit. It's known as the TOV limit, or Tolman-Oppenheimer-Volkov limit, and it's the theoretical limit where neutron stars should no longer be able to support themselves and very likely either explode or collapse into black holes. Below this limit, neutron stars still can support themselves through a quantum process of neutron degeneracy, which basically pushes things from the outside, preventing things from collapsing. But once there is enough mass, it's no longer able to do so, and should collapse, possibly exploding in the process, or possibly maybe becoming a black hole or something else. It's never been physically seen, so we don't actually know what happens. But intriguingly, not so long ago, gravitational wave detectors did actually find something a little bit more unusual. a collision between two neutron stars that produced something that's about 2.6 solar masses. It wasn't clear what the result was, but the data from this merger was pretty clear. It was an actual object. But what sort of an object is of course the question nobody can answer. And it's very likely somewhat similar to what was just discovered here as well. A result of some kind of a previous merger, possibly between two neutron stars, or a neutron star and a star, that created an object in what's known as the lower mass gap. Basically, a kind of a gap when it comes to black holes and neutron stars, where the objects seem to not exist. So for example, for black holes, we haven't really found a lot of black holes below the total mass of 5 solar masses. There are plenty of black holes that are more massive, 5, 6, 7 and so on. But to date, only one other object has been discovered that seems to have the mass of maybe 3.8 solar masses. This paper from 2019 talks about this in more detail, but even here it's kind of unknown exactly what this is. And so even though we kind of have an idea of how these objects can form, we have no idea what the result is. Is this the lightest black hole or the most massive neutron star? And if it's a neutron star, why is it not collapsing or exploding? Now we know that a fast spinning neutron star can possibly survive for a pretty long time, even if it's more massive, but when there's a partner, most spinning neutron stars do not spin very fast for a very long time and eventually slow down. And so whatever is happening here is a bit of a mystery. It's most likely a result of a merger of neutron star from previous collisions, and is obviously now orbiting another neutron star that's acting as a pulsar, but with a potential mass of 2.76 solar masses, it is currently unknown what it is. Although here the mass could be as low as 2.1 solar masses, so technically it could be just a very massive neutron star. But the exact nature of this object is going to be unknown for quite some time. Mostly because we just don't have any means right now to physically determine what it is. Either way, because this is such a compact system and very likely produces gravitational waves, this is going to be a really important system for scientists studying gravity and cosmologists trying to understand what exactly is happening in the universe and what the nature of gravity is to begin with. And that's because by studying the interaction between these two compact objects and seeing the effects they produce, it becomes possible to study everything else, including the nature of the fundamental forces. Although at the moment there is really more mysteries than answers. For example, since there is no light coming from this, not even X-rays, yet this object is definitely massive, and very likely very compact, it means that this object joins a very short list of these unusual compact massive objects that are technically in the mass gap. They really should not exist, or their existence is unexplained, yet they are out there. And so for all we know, we might have discovered a completely new type of an object we never knew existed. Something between a neutron star and a black hole, and something that maybe has an explanation already. Could this be a quark star, or maybe some kind of a dark matter star, also known as the boson star? You can learn about these in some of the videos in the description, but for all we know, since there is no other explanation for exactly what these are, these unusual anomalies and these really massive objects could actually lead us to new explanations about the nature of the universe. So today we're going to discuss some of the new discoveries in regards to the iconic pulsar known as Vela. The neutron star located somewhere right here in the Vela supernova remnant, produced approximately 11,000 years ago as a result of a Type II supernova when basically a red giant star explodes, leaving a neutron star behind. But because this happened during human prehistory, and it was also about 800 light years away from us, it's extremely unlikely that anyone wrote down anything about it. It's also extremely unlikely that anyone even noticed it, although obviously possible, and more importantly, it's unlikely that this had any effect on planet Earth. But we know it's there. As a matter of fact, here are the actual gamma rays emitted by this pulsar, even right now as I'm making this video. And this pulsar is also iconic for this beautiful observation from the Chandra Observatory of essentially what we refer to as the Pulsar Wind Nebula. A very beautiful nebula produced by the interaction of the pulsar and its very powerful magnetic fields with a lot of different material present in this area. But because this is such a well-known pulsar and also because it's relatively powerful, it's also one of the most studied objects in the entire night skies and is one of the most prominent gamma ray sources visible to various telescopes. Some of the most powerful sources are actually all pulsars or very powerful blazars that in theory can produce even more energy even though they're much farther away. And over the years quite a lot of things have been learned about this because this is basically the most studied neutron star out there. For example, we know that it spins 11 times per second and it's also the brightest persistent object producing gamma rays. but it's also a pulsar that seems to glitch quite a lot. In astronomy, when it comes to pulsars or neutron stars, glitches refer to unusual shifts in their pulsation that sometimes can be compared to, for example, some kind of a earthquake, or I guess a starquake happening on the surface of the star, which usually produces extremely tiny deviations in pulsations visible from a lot of different pulsars out there. So this is a phenomenon that definitely happens quite a lot. But in Vela pulsar, it seems to happen just a little bit more often than anywhere else. It's not entirely clear why, but that's just how things are. But I guess more importantly, this is also one of those pulsars known to produce very powerful emissions, serving as a source of some of the most powerful energy in the entire galaxy. And so it's always been kind of curious to a lot of scientists, how exactly does all of this work? And for the most part, it was believed to be understood pretty well. It was basically a result of the interaction of the magnetic field with a lot of powerful particles produced by the pulsar. But turns out that things are maybe not as we thought. Because extremely recently, scientists detected something nobody has ever expected to find coming from this pulsar. Gamma rays that were so powerful, they were completely impossible to explain. And all of this detected extremely recently, and described in detail in a study you can find in the description below. And so what exactly is happening here, and what do scientists think going on? I guess first though, how exactly did they even find this? And by itself this is actually really fascinating. In order to see these very powerful emissions coming from various locations, and so here we're talking about gamma rays for example, scientists employ these very unusual telescopes referred to as Cherenkov telescopes, whose only goal is to detect tiny variations in luminosity in the upper atmosphere of planet Earth. And Cherenkov radiation is the phenomenon that essentially makes nuclear reactors glow with this unusual light, which by itself is produced as a result of particles moving much faster than they should be moving through this particular medium. And so when certain types of radiation or certain types of particles move extremely fast through the upper atmosphere, they also end up producing Cherenkov radiation for just a tiny fraction of a second. And this is exactly what these telescopes are able to see. Any gamma rays with certain power, specifically 1 tera-electron-volts, will always produce Cherenkov radiation in the upper atmosphere and will always be detectable. And so this beautiful telescope, known as HESS, located in Namibia, has been exceptionally good at detecting these powerful gamma rays coming from various locations. But most neutron stars, or actually all neutron stars known to us, don't generally produce these types of emissions. They're not powerful enough. Things like blazars definitely do, but here we're talking about supermassive black holes. Neutron stars normally do not produce very high energy gamma rays expected to produce Cherenkov radiation. Just to give you a comparison, anything over 1 tera-electron-volts, in terms of actual energy, to some extent is equivalent to a flying mosquito. Except that here we're talking about a tiny particle, or in a lot of cases, just a single photon. So these are really powerful emissions. But at some point, once you reach approximately 10 tera-electron-volts, it even makes nitrogen in the upper atmosphere fluoresce, producing even different types of emissions, which is what many of these telescopes have been discovering in the last few years. But in most cases, the sources of these particular emissions are sort of difficult to pinpoint, though will normally end up being some kind of really powerful events such as ridiculously powerful gamma ray bursts, or in most cases, blazars, powerful supermassive black holes. These events, by the way, are kind of rare. Yet, turns out, very recently, that's exactly what the scientists discovered coming from Vela pulsar. Ridiculously powerful gamma rays, approximately 20 tera-electron-volts in power, detected coming directly from this location. Something we've never seen coming from a neutron star, and something that technically has never been seen coming from the Milky Way at all, making these the most powerful emissions coming from any source in the vicinity of planet Earth, with the amount of energy detected so far basically equivalent to a single photon with the energy of a small ball hitting the floor. That is an insane amount of energy for a single photon. And at the moment, there is no good explanation to what's going on here. Now we know that pulsars and neutron stars in general have very powerful magnetic fields, and so when charged particles are stuck inside these fields, they can actually be accelerated to a fraction of the speed of light, which very often makes them produce all sorts of light, including of course gamma rays. But in this case, the amount of gamma rays produced is just more intense than any theory ever predicted. It's really basically impossible to explain how any of this is achieved by this neutron star. And so I guess one explanation is that maybe this particular pulsar just has a much more intense magnetic field with an unusual shape such as a much wider cone, which essentially accelerates charged particles even more by having them move in a much wider circle. But even this by itself just cannot explain what's going on here. The gamma rays detected in this case are just way too powerful. This is really only something we expect from a supermassive black hole that possesses a lot more power. Not a neutron star, not a typical pulsar. With the additional explanation suggesting that, well, maybe it's a combination of very powerful magnetic fields with some kind of an effect from the stellar wind that's present around the pulsar. Here we know that, for example, materials from the previous explosion, that of course happened 11,000 years ago, is still moving really fast, at approximately 1200 km per second. And so maybe the supernova itself in this case was just much more powerful and produced some kind of an unusual geometry that allows certain particles to accelerate to much higher velocities. And so some of these high energy electrons moving around the pulsar can sometimes interact with photons nearby, dramatically increasing their energy, turning them into gamma rays. Although the overall conclusion from the paper so far is that nobody knows. And we're probably not going to know for quite some time because these are absolutely unexpected and do not match any current theory. But we might get some answers from a slightly different location that the scientists have been recently studying even more. And here we're talking about the location of the nearest supernova in the last few decades, SN 1987A, the supernova that happened in the nearby Large Magellanic Cloud, and the supernova that we're still able to see evolve even after several decades. This is at a distance of about 165,000 light-years away from us, and it was essentially a result of a blue supergiant star collapsing, creating a supernova, and very likely leaving a remnant behind. In the process, creating some of the most beautiful images we've ever been able to capture of any supernova anywhere. But interestingly, the first thing that we actually saw when the supernova happened was not the light, but the arrival of neutrinos as an unusual 12-second burst coming from the direction of this galaxy. And it was actually hours later that we finally saw some of the first light. And though the expansion of the supernova, as well as the shell itself, has been very thoroughly studied in the last few decades, up until recently, the internal structure, or basically the inner region of the shell, for the most part remained completely mysterious. Actually, the scientists even didn't know if there was any remnant left behind. Based on the mass of the star, it was expected to produce at least some kind of a neutron star, but there was just no evidence of anything, up until recently. Some of the first evidence started to emerge a few years ago, when initial observations by various telescopes, including ALMA, detected huge amounts of gas in the middle that was basically swirled by something. And there was really no way to explain this except for some kind of a massive compact object in the middle, basically creating what seems to be a pulsar nebula. Very similar to a typical pulsar wind nebula we've seen so many times before. But this was just the first sign. The most recent observations and most recent signs came from the iconic James Webb Space Telescope. Here the observations revealed something else we've never seen before, only visible with the infrared light. Unusual crescent-like formations that seem to be carved by very powerful magnetic fields. And in this case, it's extremely difficult to explain this unless there was a powerful neutron star right in the middle. And so these observations from just a few weeks ago more or less unofficially confirmed that this is a pulsar being formed right now. And basically being formed right in front of our eyes. And so in that sense, this is actually a perfect opportunity to try to understand how these objects form, what exactly happens to neutron stars to create a pulsar, and why so many of them turn out to be a little bit different. Or I guess, more specifically, when it comes to the Vela pulsar, how some of them are able to produce ridiculously powerful emissions, something that nobody has ever expected. And so by studying the iconic SN 1987A, we might have some of the first answers in the next few months. Whoa! Hey look! It's a pulsar! I guess that's the main topic of this video. Hello wonderful person, this is Anton, and today we're going to be discussing some of the recent advances and recent discoveries in regards to some of the more unusual pulsars out there. Objects that, as you might already know, are essentially extremely fast-spinning neutron stars that produce very powerful jets. Jets that once in a while we get to see from planet Earth as they shine directly at us. And though quite a few different pulsars have been discovered in the last few decades, some of them are so extreme and so unique that they actually have their own categories and their own explanations and descriptions. And extremely recently, scientists using European Southern Observatory and the Very Large Telescope released an analysis and a detailed explanation about one of the more extreme, more unique such objects, the object known as J1023, a pulsar with very strange behavior not usually observed anywhere else. So for example, in a typical pulsar, you would observe something like this. This is coming from the famous crab pulsar we're going to discuss really soon. Essentially regular pulsations in a relatively similar frequency, usually radio waves, sometimes X-rays, but in reality it can be anything depending on the environment and the overall strength of the jets, the magnetic field, and the accretion disk. We're of course seeing this because of this. The jets, as the pulsar spins, passes right through where planet Earth is. And these are usually extremely precise and almost never change in terms of frequency or even in terms of the actual period. Relatively recently, scientists using pulsars were even able to calculate precise changes in gravitational waves across the entire galaxy, detecting minute gravitational waves with extremely long wavelengths. You can learn more about this in the description below. But as always, there are some exceptions, and this pulsar seems to be one. It still has the same sort of a period, but once in a while, quite frequently, it completely changes what frequency it tends to emit. Like other pulsars, it emits radio waves for a few seconds, maybe even several minutes, just to then switch completely and emit X-rays, ultraviolet, and visible light instead. So it basically has these two completely separate phases. Sometimes it's a radio pulsar, like most pulsars out there, then it goes, nope, now I'm an X-ray optical pulsar. So yeah, it does this for maybe a few seconds, sometimes up to a minute, then switches back again. And during 2 nights of observations a couple of years ago, scientists that were studying this pulsar discovered that it did so 280 times, transitioning between 2 modes with somewhat regular periods, as if there was some kind of a separate pulsation inside the pulsar, basically making this some kind of a double pulsar. Today they refer to this as the high mode when it's in X-ray mode, or the low mode when it's just doing radio waves. But because this object is pretty far away, 4,500 light years away from planet Earth, it did take a while to finally solve this mystery. And it essentially involves, for the lack of better words, cosmic cannonballs. Turns out that once in a while, the pulsar launches these huge chunks of matter that, as they travel away from the pulsar, reduce the amount of matter around it and make the system glow less brightly, essentially only emitting radio waves. But because this pulsar has a partner, it tends to steal a lot of this gas from the partner, which then accumulates around the accretion disk and moves closer and closer to the neutron star. As a lot of this matter accumulates around the pulsar, it naturally starts to be hit by the pulsar winds that constantly flow away from the pulsar due to the fast rotation of the pulsar, but also due to the powerful electromagnetic effects. Pulsar winds are actually responsible for forming pulsar wind nebula that form these enormous structures around pulsars. These objects are really fascinating, and we'll discuss them in a separate video really soon. So yeah, subscribe if you want to learn more. And so as the pulsar winds interact with the inflowing matter, they tend to heat up all of this matter, which starts to glow in X-rays, ultraviolet or visible light, depending on the location and depending on the amount of energy. This is essentially when we see the pulsar in the high mode. But at some point, so much of it accumulates around that it's all suddenly expelled as a kind of a burp, which happens every few seconds or sometimes every few minutes, which seems to be exactly what we're seeing from planet Earth. And though by itself this might not sound too exciting, it does become more exciting when you actually start connecting this to a different type of an object that we usually refer to as spiders, or I guess spider neutron stars, although more commonly known as black widow pulsars. Here's one, I guess the most famous one, discovered a few decades ago. And these objects are really fascinating because, just as the name suggests, these are stars that are literally eating their own partners, and to the point where they actually have eaten most of the partner, leaving almost nothing behind. One of the most interesting such objects discovered a few years back essentially included what seems to be a planetary object in its orbit that used to be a star. In other words, the neutron star, or the spider, has completely consumed and expelled most of the star's mass, turning it into a planet. That older video in the description describes this in a little bit more detail, but what's interesting here is that a lot of similar systems seem to have a very similar mechanism in destroying these stars and in feeding on them. It's essentially a combination of very powerful jets and extremely powerful pulsar winds that don't just produce tiny burps, but they actually produce very powerful emissions, powerful enough to start affecting objects nearby. And so there's actually a chance that maybe this is the beginning of one of these objects. As it sort of increases its burps, and as it starts expelling more and more mass, it may eventually start producing so much that its partner is going to start losing its mass due to very powerful evaporation effects, which intriguingly leaves behind this iconic tail. The tail that can be visible from extremely far away distances and can actually be light years long. But to become a black widow or a spider pulsar, the star has to decrease in mass quite dramatically. For example, by definition, if the companion star is less than 10% of the solar mass, we refer to it as a black widow. If it's more than 10% of the solar mass, we usually call them redbacks. Okay, honestly, it's just semantics, but at least for now that's how it is. And to date, about 20 black widow pulsars have been discovered so far, but also 10 redbacks that will eventually become black widows as well. And it's generally believed that they most likely form from these millisecond pulsars, very similar to the one in this study. As a matter of fact, in one of the recent studies from 2023, Amy Knight and her colleagues discovered what they refer to as a false widow, which represents some kind of a X-ray binary where the process of ablation has already kind of started, but is not super active just yet. In other words, they actually found evidence for highly energized material around the star, suggesting that the spider phase may have already started, but it's still in early development. And so it doesn't really have that funky tail just yet, because the ablation is still inefficient, but it's already pushing away material from the star, suggesting that the star is already falling apart. And so it would be really interesting to see what connection it has to this new discovery, because it does sort of look like the beginning of such process. An even more recent study discovered another binary pulsar with the orbit of just 53 minutes, where the companion star is already only 0.07 solar masses, implying that it's somewhere between a redback and a black widow pulsars, representing yet another transition stage, and suggesting this is some kind of an evolutionary process for many binary pulsar systems. Intriguingly, its partner has technically been designated as a planet, a pulsar planet with a mass of 70 Jupiters and an orbital period of 0.04 days, although technically it would be a brown dwarf, and I guess more technically, a former star. But what's still not entirely clear is, I guess, what is the ultimate fate of these objects? What do they actually become at the end? At some point they obviously have to stop eating, and they'll probably lose a lot of energy, with the object eventually remaining permanently stuck in orbit. But what sort of system develops at the end is of course something we're not going to be able to answer for quite some time. And mostly because they will no longer be pulsars and will be extremely difficult to detect. We can obviously see them now because they produce so many powerful emissions. Once they quiet down and become just neutron stars with a planet in their orbit, that's when finding them becomes a bit of a problem. Although I'm sure in the next few years, especially because of new telescopes, we'll probably find another black widow that could be approaching its end days, allowing us to maybe calculate or find ways to calculate what all of these objects become at the end. It's definitely some kind of a binary system with potentially a brown dwarf or maybe even a Jupiter-like planet in their orbit, but only future will tell. At the moment nobody knows. But we'll definitely be able to know soon because the way we study pulsars now has dramatically improved in just the last few years. Even the iconic crab pulsar that's been studied for decades has just recently revealed more surprises. In this case, this was detected in the X-rays by using NASA's IXPE telescope, but in a nutshell it shows us that the Crab Nebula pulsar wind creates a somewhat unusual magnetic shape with extremely patchy turbulence and extremely different intensity inside of it. Even though mathematical models predicted this to be somewhat smooth, it turns out the magnetic fields here are very unusual, very patchy, very chaotic, and extremely asymmetrical. And why? Well, we don't know yet, but we'll talk more about this in that feature video on Pulsar Wind Nebula. Because even though pulsars are quite fascinating on their own, the unusual formations they produce around them, Pulsar Wind Nebula, deserve their own investigation in some of the future videos. If you somehow watched every video on this channel, by the way, thank you, you will discover quite a few videos starting with Astronomers discover incredible star. Star or planet nobody expected. Mind-blowing discovery from our own galaxy. I mean, at this point I think I'm making fun of myself. But the point here is that astronomers and scientists in general actually have made a lot of incredible discoveries in just the last few years. Many of them have been completely unexpected, and many of them quite mind-blowing. But turns out that there's actually this one star that is super mind-blowing, but that for the most part has been unfortunately ignored until now. Hello wonderful person, this is Anton. Today we're going to discuss a really exciting star that once again is somewhat unusual compared to a lot of other stars, that's now claimed to be a potential precursor to one of the most mysterious objects out there. An object we often refer to as a magnetar. A strange type of a neutron star with a super powerful magnetic field that today is believed to be responsible for a lot of other mysterious phenomena, including things like fast radio bursts or a lot of other really powerful emissions that are usually not explained. But in this case, this is just one potential explanation, because at the moment nobody actually knows exactly what's happening here, and this star seems to be pretty much unique in the entire galaxy. There's maybe one more such star in existence, which we'll discuss a little bit later. Either way, this unusual object, referred to as HD 45166 or Anger 1933, is potentially one of the strangest stars we've seen in a very long time. It's really hard to explain exactly what this is, and it's actually unknown right now how or why this star exists. So let's talk about it, and let's find out what we actually know. Now, first of all, this is obviously not the first time the star has been examined, and it was originally discovered a long time ago. But it was always believed to be a binary star with two stars in orbit of approximately 1.6 days. But because it possessed a lot of unusual properties, it was believed to be what's known as the Wolf-Rayet star, a type of really powerful stars emitting huge amounts of solar winds and producing a lot of types of radiation that very often represent the end stages of various heavy stars right before they go supernova. Although in some cases they also represent the opposite, extremely young stars that are still growing and still developing. Either way though, these are very powerful stars with very powerful emissions, super hot temperature, but are also not particularly stable, and stars that do change in time. And here, this star was believed to be one of them, with a temperature of about 50,000 Kelvin, quite enriched in helium, suggesting that it's an old star, but still possessing a lot of strange properties. And so there were actually only a few things scientists were kind of certain about. First, this seemed to be a binary system, with one star way more powerful than the other. Second of all, it was at least several times more massive than the Sun and extremely enriched in helium, with the stars orbiting every 1.6 days. But strangely enough, a lot of other chemical abundances, such as for example carbon, nitrogen and oxygen, were very different from anything we expected. Completely different from other Wolf-Rayet stars, and even different from planetary nebula or even other stars. So it's sort of like imagining finding this really bright, extremely powerful object, but the actual elements on the inside were entirely different from anything else. Likewise, by analyzing the solar wind, it seemed to be very different from a lot of Wolf-Rayet stars, and even from typical O-type stars. So here the star was emitting things extremely differently as well. And because of this, for the past few years, this was referred to as a QWR, quasi-Wolf-Rayet. A star that seems to resemble a Wolf-Rayet star, but that seems to have very strange properties. If you actually want to learn more about these Wolf-Rayet stars, check out one of the videos in the description. But the thing is, in the last few decades, only a very small number of studies came out about the star, despite its very unusual properties. For example, this was the only known intermediate mass helium star known in the entire galaxy. It possessed Wolf-Rayet spectrum, it seemed to be orbiting a B7 type star, and it was also not very massive. Although individually these properties don't mean much, together they basically formed a strange, unusual object, something that was very difficult to explain. On top of this, the way that the star was launching its wind, and the way these stars orbited every 1.6 days, disagreed with previous ideas and previous propositions about star evolution and specifically binary star evolution, once again suggesting that things here just didn't make sense. But despite of this, some scientists, like Tomer Shenar from University of Amsterdam, decided to go on a very long campaign to basically discover what the star was all about. You can actually find one of the presentations by Tomer from a few years ago in one of the links in the description, but more recently, an actual study was finally released trying to analyze and trying to understand exactly what sort of an object this actually is. With many of these new discoveries becoming possible because of the spectropolarimetry instrument known as a Shell spectropolarimetric device for the observation of stars at CFHT that was able to finally see certain things about the star no other instrument was able to see before. In the process discovering something absolutely incredible. This star seems to possess the strongest magnetic field ever seen in any type of a star that's not a magnetar, with a total strength of approximately 43,000 Gauss, or roughly around 43,000 times as powerful as the Sun. And by itself this presents both a huge mystery and of course a really exciting opportunity to explain one of the more exciting objects in the entire universe, a magnetar. Or basically the scientists now believe that this is maybe a progenitor for a typical magnetar, and they do make a pretty strong case for this. Now previously, before the study, this is what we kind of thought about magnetars. This is an explanation made by NASA. It was believed to be a different type of a neutron star produced as a result of a supernova. Some stars ended up as neutron stars, some stars became pulsars, and some became magnetars. But exactly why certain stars became magnetars and not pulsars was never really known. And magnetars, of course, are super strange. They're essentially neutron stars with magnetic fields that literally affect space-time around themselves. The magnetic fields here are so powerful that they start producing tiny bits of matter right around the magnetar. They obviously possess a lot of other strange properties, but it was just never understood why some neutron stars become this and others don't. Nevertheless, it was always believed to be a result of a type of a supernova from a star with a specific mass, possibly something similar to Betelgeuse. But the scientists behind the study did not like that explanation, mostly because they did study quite a lot of helium-rich stars before, and also because they realized something is really strange about this particular star. Now this is not the first study about the star discovering something strange. Here's another one from a few years ago, but this is the first study where conclusions finally started to make sense. First of all, they realized that the observations involving orbits of these stars might have actually been seeing something else. Before, it was claimed that this is a binary system with a 1.6 days orbit, but the new observations imply that this is actually a pulsation from the partner, and potentially even pulsations resulting from powerful magnetic fields. In reality, the orbit here was much longer. These stars were really far away, with a single orbit taking at least several years, possibly even tens of years. And the only explanation that made sense why this star was so strange and produced so many effects basically involved powerful magnetic fields. By having powerful magnetic fields, it would have unusual winds. It would also possess very strange effects observed in various studies, and most importantly, it would explain what these types of objects eventually evolve into. But because the star is pretty far away from us, approximately 3,000 light years away, it took a while before any of these observations were finally possible. And so the Franco-Canadian project using this instrument was finally able to detect strong magnetic fields coming from this unusual object. And not just strong fields, the strongest magnetic fields from any main sequence star. This basically became the most magnetic massive star ever found. But because the star was only about 4 solar masses, it meant that it's not going to go supernova. As a matter of fact, as it evolves, it's very likely going to end up in a very different state. Now, normally, in a star like our Sun, for example, as it evolves, it eventually reaches a stage where it sort of expels the outer shell, eventually becoming a white dwarf in the middle, surrounded by a planetary nebula. But in this case, as this star evolves, powerful magnetic fields are most likely going to keep it together and will eventually cause the star to collapse under its own gravity, which in the process increases the spin of the star, but more importantly, increases the magnetic field even further. And so as the star ages and decreases in size, it ends up becoming even more magnetic. And so now the scientists believe that eventually, as it collapses, instead of becoming a white dwarf, it becomes a different remnant with an extremely powerful magnetic field with approximately 100 trillion Gauss, very similar to a magnetar. And the recent observations even suggested that the mass here is probably much lower, this star could be as low as 2 solar masses, so it's definitely not going supernova. And that's how we believe neutron stars usually form. And so instead, as the star becomes older, it very likely is going to collapse further and further, becoming even more magnetically powerful, and basically eventually turning into a typical magnetar. Now by itself right now, this idea and this proposition is actually kind of brilliant. It explains a lot of things and a lot of mysteries all at the same time. But as always, because this is science, we definitely need confirmations, we need additional observations and additional studies, and more importantly, we need additional samples. More similar stars have to be discovered first in order to see if this is what's actually happening here. Now if you look at the presentation I mentioned previously, only one other similar star is mentioned in the study, but in this case it does not seem to be magnetic or possess all of the similar properties. And so at the moment it's not certain if this is the only such star in the entire galaxy, which already makes this super special and very unusual, or if there are other similar objects we're going to be discovering in the next few years. And if the scientists in this paper are actually correct, they also might potentially explain how these types of stars form. It actually seems to be a result of a merger of two smaller stars very rich in helium, which in essence may explain how magnetars are born across the entire universe. And if this is how magnetars are made, one day this might solve a lot of other mysteries, including fast radio bursts. So definitely a pretty cool discovery and a pretty cool proposition. So this is once again one of those really cool discoveries that at the moment has no good explanation. Yet another mysterious radio signal coming from somewhere in our galaxy and pointed directly at planet Earth. But unlike previous radio signals that usually have at least some explanation, in this case this one is really difficult to explain because current physical models seem to contradict what we're observing. So, hello wonderful person, this is Anton, and today we're going to be discussing a discovery of yet another periodic radio signal that was discovered completely by accident in some of the older radio data, and a signal that was apparently in that data for at least 33 years, possibly even longer. But because nobody ever bothered to check, and there was really no reason to check, as I'll explain to you in a few minutes, it remained invisible to us up until recently. As you can see, this is about 15,000 light years away from us in the constellation of Scutum. And what makes this particular radio signal super intriguing is the fact that it seems to repeat approximately every 21 minutes. And so every 21 minutes or so, it seems to emit radio bursts for approximately 5 minutes, then stops and repeats it again 21 minutes later. But surprisingly, when scientists behind the study analyzed previous radio data pointed at this location, they actually discovered that it was doing this for a very long time. With all of this data going back several decades, and the first official signal identified all the way back in 1988, and that is actually kind of impressive. This would make it one of the oldest persistent radio signals ever discovered. Obviously not the oldest, some of the pulsars have been doing this for much longer, but definitely something really impressive. But it was the more recent observations from the Australian telescopes, and specifically the Murchison Wide Field Array that you see right here, that contains these large areas of very small radio antenna, that was able to measure the signal directly, identifying certain properties that made this extremely strange. And so let's actually talk about why this is strange and why it currently has no explanation. Although here, it's important to mention why scientists behind the study wanted to even look for this, because nobody ever bothered before. We've talked about this a few years back, and I think there's a video somewhere in the description about this. But back in 2020, by looking at the older data, a very unusual radio signal was identified approximately 4,000 light years away from us. This signal was repeating every 18 minutes, lasting approximately a minute in total, but back in 2020, for some reason, this signal disappeared and was no longer observable anywhere. But based on what we've received so far, it became clear that the light here was extremely twisted, or very polarized, as if it was coming from an extremely magnetic environment. With the conclusion here being that maybe this is some kind of a really strange magnetar that we've never seen before. An extremely slow spinning magnetar that seems to rotate once every 18 minutes. But because it now disappeared and because it no longer emitted any radio signals, it was difficult to explain both its existence and why it's now so quiet. So in other words, this kind of appeared, disappeared, and was no longer heard. And so the main point behind this new study was to try to discover other additional signals very similar to this one in order to actually understand what might have happened here. And completely by accident, they discovered this new signal. This one did not disappear and has been doing so for over 30 years. And once again, this signal seems to be twisted or polarized, suggesting similar magnetic environments or basically some kind of a magnetar. The signal is now referred to as GPM J1839-10. But knowing what we know about magnetars and how they produce various jets and also how they produce radio emissions, none of this currently makes sense. And this kind of relates to the concept known as the death line for radio waves produced by magnetars. It's a type of a threshold where if a star's magnetic field is too weak, it should not actually generate any radio signals. Which is why most magnetars do not produce radio waves, or in some cases produce very weak radio waves. And in this case, this is one of the slowest spinning magnetars ever discovered. So basically here, it shouldn't actually produce anything. It's definitely below this threshold. And so because of its really slow spin, it's expected to be completely quiet, which is actually what the theory predicts and why we've never seen very slow spinning magnetars prior to this. And so assuming this is magnetar, it should really not be possible to detect these radio waves, especially because the radio waves coming from this are way stronger than anything we've imagined. So every 21 minutes, these pulses are pretty strong, actually as strong as what we expect from a typical pulsar. And so whatever is causing this currently has no mechanism to explain anything here. And because this goes beyond theoretical predictions, this is why nobody ever even bothered to look for these objects in any of the data, which is why it remained invisible for over 30 years. Now the obvious question here is, well, can it be something else? Can it be maybe artificial? Can it be aliens? Not really. Even this image alone kind of shows you that a lot of these signals are very hectic, very chaotic, and do not have any particular pattern or anything artificial in them. They do appear very natural. The observations so far basically resemble a typical pulsar, just kind of in slow motion, pulsating very, very slow. A regular pulsar would be doing this at least several times per second, sometimes even several hundred times per second. Some pulsars are very fast. And so this is like thousands and thousands of times slower. And so if this is a magnetar, it really kind of defies all the explanations and all of the physical concepts we currently have. So maybe this is some kind of an unconfirmed, unusual type of star we've never seen before. If so, it's not really clear what this is. Now, previous explanations about the previously discovered object from a few years back, apart from a magnetar, proposed another explanation. Maybe this was actually a strange and never before seen white dwarf. A pulsating white dwarf that was producing very powerful radio emissions, and in this case using a slightly different mechanism. Now if this is a white dwarf, it would be basically the second one ever discovered doing this in such a way, but even here the explanations would still require additional physics that we currently do not have. Why is it so powerful? How is it able to do so regularly and with such a power that it's visible from 15,000 light years away? And more importantly, why do other white dwarfs not do the same? On top of this, it seems to actually spin quite regularly, and the observations suggest that it's not really slowing down very much, and it's essentially doing everything we kind of expect from a typical pulsating radio object. And because several different telescopes were able to confirm its existence and exactly what we're observing here, at the moment, it seems to be pretty clear that it's there, and unlike previous discoveries from magnetars, which sometimes actually stop their emissions after a few years, this one just keeps going. So yeah, what exactly is this? What exactly did the team behind this just discover? Well, whatever this is, it's going to be super exciting to talk about this in some of the future videos. As I mentioned in some of the previous videos, we've basically now entered the golden age of radio astronomy. There's a tremendous amount of new discoveries, most of them completely unexplained and have just been discovered in the last couple of years, and the vast majority right now are basically showing us the entire universe in a way we've never seen it before. You can check out some of these radio discoveries in the description below. Here we're talking about things like orcs or odd radio circles. We're of course also talking about fast radio bursts, or the most recently discovered Sauron. Yeah, a lot of them have been given really cool fantasy names. And now we have another addition. It doesn't have a cool name yet, but definitely deserves one. But all of these incredible new discoveries are actually all the result of a sudden explosion of additional radio observatories across the entire planet, especially really large ones in South Africa, a lot of them in Australia, with the biggest dish currently being in China. All of this was actually completed in the last few years, with more being built even right now, and so we're only going to be getting more mysteries and more unusual discoveries in the next few years. Hello wonderful person, this is Anton, and today we're going to be discussing a somewhat intriguing paper that suggests strange stars actually exist. And here it's actually kind of difficult for me to even help you visualize this. We're not really talking about stars that are just weird or strange. We're talking about stars or objects made out of what's known as strange matter, which by itself is made out of what's known as strange quarks, essentially matter that does not exist here on planet Earth, or I guess technically could exist for like a microsecond in some kind of a particle accelerator, but theoretically has always been suggested to be a possible type of matter that could exist inside, for example, neutron stars, or might have actually existed in the beginning of the universe, with hypothetical objects known as strange stars still in existence today. But in this case, we're going to be discussing this particular study that's actually a follow-up or an additional observation from another previous study, the one you can find in the description below, that seems to have confirmed these initial observations. Basically confirming that the observations from the supernova remnant located somewhere right here seem to indicate that there is an unusual object in the center whose current physical properties are extremely difficult to explain using modern physics, implying that this unusual object has a very high chance right now to actually be the first ever confirmation for an existence of very exotic objects. In this case, the objects were referred to as strange stars. But I guess let's start with baby steps. So here's how all of this kind of started. It basically all began with the discovery of a new supernova remnant. And as you might already know, most supernovae usually result in one of two things. Either some kind of a black hole remnant, what we usually refer to as a stellar mass black hole, or potentially a neutron star. And it's really the mass of that initial star that went supernova that determines what's going to be produced. More massive stars result in black holes, less massive stars result in neutron stars. Although actually extremely massive stars can sometimes leave nothing behind. But that's something that only happens to some of the most massive stars we've discovered so far, and as a matter of fact has never really been seen physically either. Nevertheless, remnants, including neutron stars and black holes from various supernovae, have been seen many times. But when looking at this particular supernova remnant that was discovered a few years back, the scientists using various telescopes and using multi-frequency observation discovered something unusual on the inside. Okay, it wasn't really unusual at first. It became unusual with further analysis. It seemed to be the lightest neutron star ever discovered, or the least massive neutron star ever discovered. But in this case, way below even theoretical mass. And this would have been totally fine and not really a problem if this was a white dwarf, because white dwarfs typically have this mass of about 0.8 solar masses, but this would create a new problem. A supernova cannot possibly produce a white dwarf unless it's a type 1 supernova, where a white dwarf explodes but does not explode completely. But this was not the case. All of these emissions indicated a type 2 supernova, and the emissions from within, specifically the X-rays, indicated that this was not a white dwarf but very likely a neutron star after all. But the thing is, this wasn't really a problem until recent observations from the Gaia telescope. Because at first the scientists believed that this was a regular neutron star, but turns out that their distance calculations were incorrect. When Gaia telescope recalculated the exact distance to this object using some of the most advanced astrometry technique that we currently have, the distance was determined to be approximately 8,150 light years away from us, not 10,000 light years as previously assumed, which implied that the central object was not as massive as initially thought, and really implied that this was the lightest neutron star ever found. Previous measurements of its mass were actually much higher. But the thing is, the current models for the star collapse do not allow for such low mass neutron star. With so little mass, it really can only be some kind of a white dwarf, at least according to previous theories. As a matter of fact, the lightest neutron star that's accepted by everyone to date is a neutron star located in the Pulsar binary. In this case, the lightest object is about 1.17 solar masses, and even here that lower mass is a bit of a problem. But at 77% of the solar mass, it really makes no sense whatsoever. So what exactly is this object then? And at the moment there seems to be only one potential explanation that kind of makes sense. It's really in regards to how matter changes when it finds itself in extreme conditions of high pressure and very high temperature. Now we're all familiar with ordinary matter, the stuff that we have on Earth. That's the stuff made out of atoms, sometimes also referred to as atomic matter. But as you go deeper you find nuclear matter. It's sort of like a liquid composed of neutrons and protons, that by themselves are made out of even smaller stuff, the stuff we refer to as quarks. And everything around us that we're familiar with is made out of up quark and down quark. But there are obviously other quarks. Specifically, there are strange quark and charm quark, sometimes also referred to as the second generation quarks. And the combination of strange quarks with, for example, up and down quarks starts to produce other subatomic particles, which have been used to explain a lot of other phenomena in various particle physics, with a lot of these calculations and explanations generally being in the domain of condensed matter physics or quantum chromodynamics. And so some of the theories in this field propose the existence of what's known as strange matter. Basically matter that's composed of strange quarks, remaining in a stable state and not dissolving into anything else, unlike in regular conditions on planet Earth. And in this case, a lot of these theories have actually proposed that this type of matter can definitely exist inside neutron stars in extremely dense, very hot conditions, where basically matter dissociates into quarks, creates what's known as quark matter, and some of this quark matter then starts to convert into specifically strange quark matter, eventually creating this relatively permanent matter that doesn't actually dissociate into anything else. Another way of seeing this is by imagining a neutron star as a kind of an ocean of neutrons, with all of the quarks in this neutron star confined into individual neutrons. But at some point, in just the right conditions, this confinement disappears and creates free-floating quarks. This is what we refer to as a quark star. But as a lot of these up and down quarks start to convert into strange quarks, potentially creating a more stable structure, they then turn into this hypothetical strange star. And what's really intriguing about this proposition is that it suggests that this particular object might actually be a permanent structure. This refers to an idea known as strange matter hypothesis. And in this case, the hypothesis suggests that pretty much everything around us, all other matter, is not permanent. It decays over time and becomes something else. Or basically, a lot of matter is metastable. Given enough time, even nuclei and protons and neutrons around us are going to turn into something else, eventually maybe even becoming just energy itself. But not strange matter. Droplets of strange matter seem to be permanent and do not disappear. These droplets are sometimes referred to as strangelets. And in the last few years, the scientists identified at least 8 potential candidates to be these unusual strange quark stars. And the most exciting candidate we've discussed just over a year ago, with the video in the description. But the recent additional observations of this unusual object once again confirm that something here does not add up. It does not seem to be a regular neutron star, and so by double checking the mass, the radius and the surface temperature, and comparing this with equations that involve some kind of a strange matter, these models seem to actually align with the observations. Hess J1731-347 might be a strange star after all. Although in this case, it would still have some neutron matter on the surface, so it still possesses certain properties from a neutron star and still creates certain effects. But if this is the case, it's still not clear how exactly this object was produced. There is really no theory or no explanation for how a supernova can result in the production of this unusual object and what processes led to the production of a strange star and not just a neutron star. One proposition is that for some reason there might have been even more energy in the collapse that resulted in the removal of the mass, leaving a huge amount of quarks behind. But some other models even propose that maybe this is actually something that all neutron stars possess, but in this case the neutron star might have just lost its outer shell, leaving behind nothing but the quark star or the strange star. Whatever it is, still really exciting and will probably result in even more observations in the future. Although in this case, if this is actually a strange star and if it's real, it potentially solves another really important mystery somewhere out there in the universe. The mystery of fast radio bursts. Powerful radio signals detected from everywhere in the universe, pretty much several times per day, whose existence have been previously explained as a potential collapse of the crust on top of the strange stars. So if that tiny crust of neutron matter collapses on the surface of a strange star, it can actually result in what the scientists describe as a fast radio burst. And because we've been seeing so many around us, and because many of them still do not have a very good explanation that explains all of them all at once, some theories propose that maybe this is a strange star phenomenon after all. A few years ago, one of the major discoveries coming from the gravitational wave detectors was the detection of a neutron star collision. 2 neutron stars on a collision course in a really faraway galaxy produced very intriguing observations that the scientists studied for several months afterwards, in the process confirming something the scientists have been expecting for a very long time. These types of collisions seem to be responsible for the production of a lot of heavier elements that we generally take for granted here on planet Earth. For example, things like gold and platinum and a lot of other heavier elements. So all of this was actually a result of a collision between two neutron stars in the Milky Way galaxy, very likely in the vicinity of planet Earth, that somehow managed to enrich the material that planet Earth was made from, and all of these materials are now being basically worn by us. By itself, a pretty mind-blowing concept. But obviously this was not the only discovery, and a lot of research has been done since. As a matter of fact, not so long ago, NASA released this absolutely incredible simulation showing us this initial collision, but this time with a kind of a sonification of gravitational waves, allowing us to understand how all of this very likely sounded, and what sort of effects were produced through the gravitational interaction of the collision that happened here. Take a listen. So these unusual oscillations and reverberations, echoing and whistling, is basically a result of two different tones oscillating in frequencies of thousands of hertz. And it's the oscillations produced by the final object that results in a merger, possibly right before the final black hole forms, and very likely when this object becomes some kind of a really massive magnetar. Although the actual answer is still unknown even today. But whatever this object was, it was producing these unusual tonal frequencies, which were then heard by the gravitational wave detectors. But ever since that original detection, the scientists just wanted to understand more, and they wanted to answer some other questions. For example, how often do these happen in the Milky Way, and do we know of any potential candidates right here in the Milky Way galaxy, so we can actually study them more? Because, as I mentioned, this is believed to be a major factory for a lot of heavier elements detected on planet Earth. And, well, hello wonderful person, this is Anton, and it looks like the answer to that is yes. The recent identification of an unusual supernova that happened in a star system not so far away from us most likely definitively showed the scientists that this is actually a progenitor for such an event. And so let's discuss this particular study and the discovery in more detail, and talk a little bit more about what sort of star systems usually create this. Because they all seem to have a relatively similar origin, and it seems to involve two stars, a binary system. But I guess first a little bit more about this detection. So a few years ago, back in 2016, one of NASA's X-ray observatories detected an unusual explosion from a location with a known BE-type star. These are generally very active, very bright stars, often with a partner and often containing a lot of materials around them, producing very specific emissions. For example, this is Gamma Cassiopeia, one such star. But the analysis of the supernova revealed that it was what's known as ultra-stripped supernova, extremely weak and barely producing any emissions. And it happened at a distance of 11,000 years, yet was barely visible. Moreover, when the scientists observed this afterwards, they realized that the initial star was still there, so it survived the explosion. But because BE stars very often contain a relatively thick envelope around them, it's usually hard to see what's going on here. Nevertheless, the scientists were really curious to find out what's really happening here. Which meant that the scientists had to conduct more follow-ups, more observations, with the scientists really trying to figure out why did this star did not go completely supernova, and more importantly, why did it look like almost nothing here changed. As a matter of fact, the orbital analysis in this case determined that even the orbits of the binary system have not been affected at all. Normally, a supernova explosion will at least dislodge one of the stars, or change their eccentricity, or do something. But the same was not observed in this system. As a matter of fact, the scientists confirmed that in this case, the two stars had a very unusual circular orbit, not even elliptical, and were circling around each other every 60 days, implying a relatively close orbit. But more importantly, they confirmed that one of the stars was larger than the other star, and so because of the overall close distance, and because of the overall large mass, the actual explanation started to make sense a little bit more. In this case, because of the distance, it's quite likely that one of the stars started to steal material from the other star. And it was probably done because that larger star started to expand quite dramatically, and its envelope started to touch the surface of the smaller star. This is something that's been observed and studied in a lot of other star systems as well. And so over time, that larger star shed quite a lot of hydrogen to its smaller partner, which very likely grew in size from being about 8 solar masses to maybe about 18 solar masses, practically doubling in mass, which is already quite impressive. But it also meant that its larger partner was actually now the smaller partner, and because it was basically approaching the end of its cycle, it was reaching the point where it was about to go supernova, with the resulting explosion being extremely low in energy, not enough to kick the star from its orbit, and not even enough to produce enough light. But in the end, it did end up producing a neutron star in the center, which is kind of where we find ourselves now. We now have a relatively large and a relatively giant star, possibly 18 to 19 solar masses in total, that consume the mass from its partner, and then we'll have a neutron star next to it, with an orbit of approximately 60 days. But here's the thing though, because that partner is now also very massive, in the next million years or so, it's going to start experiencing pretty much the same. As it starts to expand itself, now the neutron star is going to start stealing its mass back. But instead of depositing the mass like a typical star would, it's most likely going to release all of this as a really huge envelope around the binary, very likely producing a very beautiful nebula. And then within about a million years from now, we're going to have another strip supernova, this time of its partner, with all of this possibly happening within the next 7 million years, with the final product being two neutron stars in pretty much the same position where they were initially, basically creating the progenitor of so many neutron star collisions we've been observing from other galaxies. And at this point, they're going to remain this way for a pretty long time, possibly at least 2 billion years. But because of the gravitational waves, they're slowly going to make their way closer toward each other, and eventually, after a couple of billion years, will reach the point where they're going to collide, producing even more gold, even more platinum, and a lot of other heavier elements, resulting in what the scientists refer to as the kilonova, making this a very unique star system in the Milky Way that basically is going to have 3 separate supernova events, with all of this ending in some kind of a black hole after a few billion years. But most importantly, finally identifying almost definitive candidate for these very unique and very rare events we've been seeing from other galaxies. Hello wonderful person, this is Anton, and today we're going to be talking about a relatively interesting and somewhat unusual discovery of what happens when two neutron stars collide and what effects this produces as a result, something that the scientists really did not expect. And to be more exact, we're going to be discussing new observations coming from the iconic neutron star collision that produced a kilonova. An explosion very similar to a supernova, but usually not as powerful, but also responsible for the formation of a lot of elements that we generally consider to be very precious here on Earth. For example, it was discovered to be the main source of things like gold, platinum, and so on. But this particular collision seems to have resulted in something else the scientists really did not expect. It didn't just explode like what you're about to see in this simulation by NASA, it ended up producing a very unusual shape as a result. Not the same as you see right here. This is a predicted shape. Instead, this explosion resulted in a perfectly spherical shape. Something that at the moment the scientists really cannot explain, and something that definitely goes beyond our expectations, and also potentially means that there's something about neutron star collisions the scientists still don't understand. And so let's discuss these discoveries and what they mean for modern science, but I guess let's start with how all of this was detected and how this began a completely new era of modern cosmology. This was actually only a few months after the detection of the first black hole collision by one of these detectors, very similar to the one you see right here, which is called Virgo. This one is in Europe. This first black hole collision was such a groundbreaking discovery that it started to transform how we understood reality about other collisions as well. And the collision that they were really interested in discovering was the one between a black hole and a neutron star, or better even, two neutron stars. But nobody knew how frequent these are, but more importantly, nobody knew what effects this is going to create if one day we discover one of these somewhere out there. To everyone's surprise, sometime in 2017, both LIGO detectors and the Virgo detector discovered something unusual coming from the galaxy that you can kind of see right here, or at least the vicinity of this galaxy, somewhere around this area. Intriguingly, around the same time, the gamma ray detectors have also picked up something really powerful happening in NGC 4993, the galaxy you see right here. This was a very intriguing explosion, very different from a typical supernova, producing an extremely powerful gamma ray, which has always been predicted to be a result of neutron star collisions. But much more importantly, all of this happened approximately 1.7 seconds apart from the detection of gravitational waves. And for these two events to happen coincidentally in the same region is practically impossible, which meant that this was probably caused by the same event. Something collided, it was detected by gravitational wave detectors, and it was then picked up by various telescopes, first gamma ray detectors, and later other detectors as well. And because this was such an exciting event, huge amounts of data were collected during those few days. It also resulted in several different publications, including this one you can find in the description, and just generally resulted in so many different ideas, studies, and theories proposed right after this detection that you can kind of see right there with this time-lapse from the European Southern Observatory. Although I guess more ironically, it also sort of presented a major problem for a lot of alternative theories of modern physics. The biggest one was MOND, Modified Newtonian Dynamics. It tries to explain dark matter by essentially changing the gravitational formula, and one of the biggest predictions in this theory is that gravitational waves should be traveling at very different speeds compared to electromagnetic waves, which means that according to this idea, the gravitational waves coming from this particular explosion should not have come within 1.7 seconds apart from the actual visual observations. And so following this observation, this particular idea faced itself with a major discrepancy it could not explain even today. But more importantly, as I mentioned before, the scientists learned that this particular explosion also created so many different heavier elements, and not just platinum, not just gold, also a lot of other stuff, like for example strontium. And though it might not sound as exciting as gold and platinum, apparently so much strontium was produced in this explosion that the scientists were then able to generate a kind of a geometrical shape based on the elemental detection itself, or essentially they were able to see how these elements were spreading away from the explosion and what kind of a shape they formed as a result. And well, everyone expected maybe something like this, some kind of a bidirectional shape or possibly some kind of a flattened shape similar to what you see in the simulation from NASA, with this obviously being the gamma ray produced by the explosion itself. Now, all of this is based on many different simulations, computer simulations, that have always ended up creating these unusual pancake shapes. And that's sort of what the scientists expected, except that this is not what they saw from this observation when they looked at strontium. It seemed to produce something like this. Very spherical, almost perfectly spherical, almost resembling a ball. Now this is more of an artistic recreation, but this is based on mathematical models and all of the data collected over the past 5 years. You can find the actual numerical values in the paper in the description. But it really makes no sense for the scientists why it ended up releasing a ball and not some kind of a pancake. The detection here suggests that there's something we don't understand about the actual collision, and specifically probably something that happens right before the explosion itself. And so it's possible that up until this point, we understand most things, but right here something happens that results in the formation of a very different shape. The moment right before the collision, when they start spinning around one another several hundred times per second, something must happen inside the neutron stars to suddenly have them become a perfectly spherical object. Because it's really the only way we can explain why they end up releasing things in a ball formation. With one potential explanation here being that maybe there's just way more energy in the center of the collision that ends up creating a perfectly spherical shape that would be otherwise somewhat asymmetrical. Or in other words, significantly more energy is generated by the resulting collision compared to all of the simulations in the past. And specifically right before they collapse into a black hole, because that's usually their fate after just a few milliseconds. And so right before the final collapse and the formation of a black hole in the center, previous studies have actually suggested that maybe these two neutron stars form some kind of a very massive, very powerful magnetar, sometimes referred to as a hypermassive neutron star. And so for maybe just a fraction of a second, the neutron stars form a much larger, much more massive object that actually seems to maintain itself through extremely powerful magnetic fields. Or basically, it avoids collapsing into a black hole, maybe for just under 1 second, because its magnetic fields are so ridiculously powerful and because it just spins ridiculously fast. But because its mass is higher than what should be possible, even the magnetic fields at some point collapse, which the scientists think might create some kind of a magnetic bomb. A huge explosion, dramatically magnified by the magnetic fields, with the enormous energy from the magnetic fields then released as the star collapses into the black hole. But it's the magnetic field that causes this perfectly spherical shape. And since strontium in this case is one of the lighter, heavy elements created in these explosions, it's produced in much higher amount and is also obviously much easier to see. And since the scientists expected to find a lot more heavier elements in this case, but instead discovered a lot more strontium, it implies that the explosion in this galaxy was very different in nature from what the scientists expected. And so not just spherical in shape, but also possessing elemental composition very different from what the scientists predicted, with neutrinos probably playing the most important role. But what's the main conclusion? Well, the main conclusion is that this explosion showed us we don't actually understand how neutron star collisions and following explosions actually physically work. There's still no clear indication of what happens right at the end of the collision and what happens before the black hole is formed. And more importantly, what kind of an object is generated for just a microsecond right at the end of the collision, and what effects this further on has on the explosion itself. But because this detection and explosion produce so much data that's actually still being analyzed even today, it's only a matter of time before the scientists discover something else unusual coming from this area, from this galaxy, approximately 140 million light years away from us. With the overall conclusion from various studies really implying that all of this results in some kind of a ultra-powerful magnetar, a hypermagnetar, that exists just under 1 second, collapsing with very powerful effects, that at least in theory could maybe exist even longer, somewhere out there in the rest of the universe, and maybe even not collapse into a black hole after all. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new unusual discoveries in regards to neutron stars, but more specifically in regards to a very unusual type of a neutron star known as a magnetar, something that today is used for a lot of different explanations of other mysteries, such as various unusual radio emissions known as fast radio bursts that seem to come from all over the place for unknown reasons, or some other unusual emissions that cannot be explained in any other way. In other words, today magnetars are basically kind of like a scapegoat for when we just don't really understand what's happening somewhere out there, with the only explanation being that some kind of extreme physical environment created by these objects seem to produce various types of emissions and various types of mysteries that currently cannot be explained otherwise. But in the last few months, a few interesting observations and theories have been proposed about magnetars, and also other neutron stars as well, that help us understand that, well, basically these are just really strange objects, very unique, and something that we cannot even wrap our heads around. But first, a brief reminder of what these objects are. So following a supernova of a certain type of a star, usually a star that's massive enough to produce a neutron star but not massive enough to produce a black hole, some of these objects, in some really rare cases, will actually end up producing what's known as a pulsar, of which we've actually discovered several thousand, and that's essentially a neutron star that spins really fast, and also produces astrophysical jets which then can be visible from very far away distances. But in some really rare cases, it can also produce a magnetar, the most powerful magnet in the universe. Something that's so extremely powerful magnetically speaking, that it actually starts producing some ridiculous effects right around it, especially close to the surface. For example, one of these effects starts affecting space-time itself, the fabric that we are basically in. The empty space around the magnetar, first of all, starts to produce all sorts of particles because of ridiculously powerful magnetic fields around it, and because of the famous E=mc². But second of all, it also changes the properties of space around itself, turning it into almost like a lens that starts to refract light and even produces mirror images, in some sense producing very similar effects to what we kind of expect from, I guess, a crystal, although in this case there is no crystal, it's just space itself. But now the scientists have also realized that this magnetic field seems to affect the surface of the magnetar itself. It changes the properties of the surface to essentially make it extremely strange and very counterintuitive. The surface in this case seems to actually become solid, kind of like, I guess, a terrestrial planet. Although really not, because here we're talking about some of the most extreme environments in the universe. But all of this really being the result of super powerful magnetic fields produced by these unusual objects. The objects that were only theoretical up until a few decades ago. And theoretically, these objects were initially used to explain what's known as soft gamma repeater. The events that were detected back in the 70s and were detected several times since, but that could not really be explained otherwise unless there was some kind of a very magnetized neutron star creating all of these emissions. And actually the most famous of them all today is the one that happened in the Milky Way galaxy back in 2014, and the one around which we then also identified an actual fast radio burst, FRB. And that's how the scientists were initially able to connect these two events, with basically magnetars potentially explaining both mysteries at the same time. But one of the reasons why we think there aren't really that many of them out there, and also what we think eventually happens to magnetars, is that they have to, at some point, lose all of their magnetic field through the emissions of various gamma rays and X-rays over a period of several thousand years. This is of course how the scientists explain their evolution, and also why we don't really see a lot of them out there. As of today, only just over 30 of them have been found so far, making these some of the rarest objects out there. And because the scientists believe that millions of neutron stars must exist in the Milky Way, but basically are difficult to find because they don't emit any light, the fact that there are only 30 Magnetars out of millions and millions of neutron stars obviously makes them extremely rare. But it's really because of these ridiculously powerful emissions that can be visible from millions of light years away that the scientists were able to identify them. And it's also the reason why eventually they're going to become extremely silent. All of this energy is eventually going to dissipate across the universe. And one of the most well-studied Magnetars, and one of the closest ones to us, is the one whose name you see right here. A Magnetar that the scientists have used for a lot of different studies already, and was the Magnetar where the scientists were able to finally see the phenomenon of vacuum bifringens. The phenomenon that changes the property of vacuum into something resembling a crystal, even though there is nothing on the inside, but the light does create mirror images. Now, since this Magnetar is about 13,000 light years away from us, or basically one of the closest ones we've discovered, a lot of modern telescopes, especially X-ray telescopes, often focus on this Magnetar in order to try to solve some of the mysteries of these strange objects. One of these telescopes is NASA's IXPE, that spends several days looking at this particular region, trying to get as much data from the Magnetar as possible. But this time, for the first time ever, getting polarized data of the X-rays coming from the Magnetar itself. In the process, discovering two really unusual things. First, the light coming from here was not as polarized as the scientists expected, which suggested that this Magnetar very likely had no atmosphere whatsoever. Now, we know that a lot of stars have atmospheres. For example, our Sun obviously does, but so do a lot of other stars, and even neutron stars. As a matter of fact, not so long ago, the Chandra telescope was able to observe X-rays coming from another neutron star, discovering that there was an atmosphere that's approximately 10 centimeters thick. But the polarized light coming from here suggested that the atmosphere turned into something else. And in this case, by looking at slightly different frequencies, they actually did see polarization changing by exactly 90 degrees. Which in this case matched a theoretical prediction for if there is a solid surface on a Magnetar, but definitely not a solid surface that we have here on planet Earth. As a matter of fact, it's practically impossible for us to imagine what's going on here. But the more intriguing part is the explanation. Here, the scientists believe that the extremely powerful magnetic fields sort of made the atmosphere turn into a solid. In other words, it's almost as if the atmosphere froze over, turning into a kind of ice. Once again, it's the only analogy we have because, in this case, these are some of the most extreme types of matter that we can't even imagine. But the analogy of ice is really the only one that currently makes sense. Although in this case, the scientists believe that the temperature probably played at least some role as well. With the suggestion being that maybe this neutron star was just a little bit too cold for it to have an atmosphere. Instead, everything solidified, turning into a kind of a crust around it. To try to confirm this, the scientists would have to find a very similar Magnetar in terms of magnetic field, but with a slightly different temperature, and if they actually see the atmosphere around that Magnetar, especially if it's hotter, this would maybe give this hypothesis a little bit more credibility. And so at the moment, this idea of magnetic condensation, or basically turning into solid because of super powerful magnetic fields, at least for now, is a proposition and a hypothesis, but not really a theory. Although I guess what's really intriguing is that in this case, this particular Magnetar seems to have at least two very unique, very strange phenomena happening around it. Magnetic condensation and vacuum birefringence. Both of them because of ridiculously powerful magnetic fields. And the natural question here is of course to try to imagine what the surface would even look like, or at least trying to imagine what sort of particles it's probably made out of. Now, since we're talking about the neutron star, it's obviously made out of neutrons on the surface. But in this case, because of the magnetic fields, these neutrons are probably arranged in a very specific order along the magnetic lines, but also very likely acquire their own charge, essentially creating a very specific structure that follows the magnetic lines, but also a structure that's ionized even though these are neutrons. Or at least that's the guess for now. I'm sure it will change in the next few years. Intriguingly enough though, this is not the only discovery about neutron stars that was made in the last few months. Another discovery in regards to surfaces and the internal structure
comes from the other non-magnetized neutron stars that we've discovered many times before. And in this case, the discovery is purely mathematical and theoretical. It was essentially done by trying to calculate the speed of sound inside of a typical neutron star-like object. And in the process, the scientists discovered that based on the mass of the neutron star, it might actually possess very different properties. In this case, much heavier neutron stars will very likely have much stiffer mantle and extremely soft core, whereas the lighter neutron stars will have soft mantle and extremely stiff core, with the example that the scientists provide being pralines, chocolate pralines. And so it seems that, depending on the mass of a neutron star, they might actually form slightly different objects, with the mass limit in this case being approximately 1.7 solar masses. So anything more massive starts to acquire much more solid surface and much softer insides. Anything less than 1.7 solar masses remains much more solid on the inside. But naturally this has to be confirmed through observations, and it hasn't been done yet. This is all just pure math for now. Nevertheless, a pretty intriguing discovery. Neutron stars are already pretty strange. They're some of the strangest things in the universe, possessing a lot of properties and a lot of qualities that we actually have trouble explaining, and also representing some of the most extreme objects and some of the most extreme matter in the universe. Matter that we still have trouble explaining even today. As a matter of fact, except for maybe the outer shell, the shell that the current physics models can actually kind of explain, everything on the inside becomes more or less mysterious and practically impossible to understand or to explain. We don't entirely know what's inside the neutron stars, but it could be exotic matter that doesn't exist anywhere else in the universe, and matter that can help us solve so many mysteries about the universe if we can actually understand it. Hello wonderful person, this is Anton, and today we're going to be discussing this relatively new study that might have discovered something extremely unusual that we've never really seen before. Either the lightest neutron star or the least massive neutron star we've ever seen, or possibly an exotic star, maybe even a Quark star, something that the scientists have speculated existed somewhere out there, but something that we haven't seen up until now. So let's talk a little bit more about this, because it is a relatively interesting discovery. But it's actually not a new discovery. We've known about this object for quite a long time. What's new is the analysis that determined we might have miscalculated something. But the object itself is a supernova remnant originally discovered back in 2007, representing a typical remnant with what seems to be a neutron star right in the middle. Although even if we zoom in here, it's still kind of difficult to see anything, especially in the optical light, which is why it did take a while to discover this. But all of these original calculations determined the distance to be over 10,000 light years away from us, making this a relatively far away object. However, you probably know by now that measuring distances in space is always a bit of a challenge and sometimes is extremely tricky. And it was particularly tricky in this case. So up until now, the actual distance was more or less an assumption. But using some of the newer telescopes and some of the newer observations, the scientists started to discover new objects in this region. Specifically discovering new stars potentially interacting with the gas left from the supernova. And one of these stars was optically bright. And this optical bright star allowed the scientists to determine the distance extremely well, because of one single telescope. The ESA's Gaia telescope that's been doing an incredible job at essentially collecting a lot of astrometry data and producing extremely accurate maps of star motion across the night skies, which of course included this particular star. And so the scientists were able to recalculate the distance, determining that all of this was approximately 8,200 light years away from us, much closer than initially assumed. Which also meant that the properties of the neutron star that was found here had to be recalculated as well. Because it was much closer, the emissions that were assumed to be 10,000 or even more than 10,000 light years away from us had to be produced by an object with a different mass and very likely different size. And so combining knowing what we know about neutron stars in terms of their size and their mass, mixed with the observations from this particular object, the scientists were able to redefine its mass and its size to something we've actually never seen before. This was about 10 kilometers across, which is actually not unusual for neutron stars, but its mass was approximately 0.77 solar masses, which would make this the smallest and the least massive neutron star we've ever seen. But a neutron star that kind of poses a problem. It's sort of below the theoretical value, and it's way smaller than anything we've ever seen. Most of the neutron stars are usually about 1.4 solar masses. The most massive one discovered to date was about 2.3 solar masses, and that was also kind of pushing the limit. And the smallest one before that was about 1.17 solar masses, with the theoretical lowest value being 1.1. Below that value, neutron stars are believed to be kind of impossible. Yet here we had something that was about 70% of that value, with the size also being much smaller as well. And though at first the scientists thought that maybe it's a white dwarf, simply based on its mass, the emissions coming from this object seem to suggest that the size is much smaller and the actual X-rays are much stronger than anything from a white dwarf, suggesting that it's a much more compact object, sort of appearing as a neutron star. But a neutron star that theoretically is not really possible, which kind of creates a bit of a problem and a bit of a mystery. Now it's possible that our calculations for neutron stars might need to be reworked in order to really understand how small these objects can form, with obviously previous problem being caused by the largest neutron star found. We've discussed this in one of the previous videos in the description, with a much more interesting explanation here being that maybe it's not a neutron star. Maybe it is some kind of a hypothetical object that we've never seen before, or potentially the mysterious Quark star the scientists have been looking for a very long time. A star that's also sometimes known as the strange star, essentially made out of strange quarks. Now they're not actually called strange quarks because they're unusual, they're actually called strange quarks, with their partner being called the charm quark. And these are quarks that we know exist, they've been detected many times, and theoretically they've been proposed to be able to create what's known as a strange star, a star that in theory should be stable enough to exist for a very long time, but actually possess very different qualities and very different properties to anything that we know and see around us. We've briefly discussed this in another video in the description. Now right now it's obviously unclear if this is one of these stars because the properties of these stars are still unknown to us, and obviously because of the distances involved here, it's kind of difficult to determine all of this. But at the moment, at least in terms of theories, if this star is indeed 0.77 solar masses, physically it's very unlikely to be a neutron star. And the only other compact object we can think of that can qualify as what we're observing would be this unusual Quark star or strange star. Mostly because it's believed that Quark stars would not really have a lower limit and can actually possess quite a low mass compared to a neutron star. However, the emissions coming from this object still kind of make it appear as a neutron star, so basically it's a bit of a mystery. Now here it's still possible that maybe something was miscalculated, for example maybe the emissions or the distances once again, but as it stands right now, it's a pretty exciting mystery. It's a mystery that we don't really know how to answer because either this is the smallest and physically impossible neutron star, a neutron star we've never seen before, or this is not a neutron star but instead some kind of an unusual exotic object, very likely a strange star or a Quark star, or, and this is where new studies will probably answer this question, something here was a mistake. There was a miscalculation in one part or another, with the object maybe being a normal neutron star, just misinterpreted as something smaller. Nevertheless, a pretty exciting paper, and potentially a paper we'll be coming back to when the scientists figure out exactly what's happening here. There are quite a lot of mysterious, fascinating, and somewhat scary objects out there in the universe, with some of these objects being so powerful that they're able to destroy everything around them, in the process absorbing a lot of mass and a lot of energy from the objects they're destroying. This is one such object. Hello wonderful person, this is Anton, and today we're going to be discussing some of the most recent discoveries in regards to these very peculiar and somewhat terrifying objects known as the Black Widow Pulsars, or sometimes just known as Black Widows. The objects of absolutely ridiculous power, able to basically destroy any star, any planet, anything in their vicinity. And through this destruction, they actually absorb a lot of this into themselves, becoming more and more powerful in the process, but also, at the same time, potentially solving one of the longest mysteries in regards to certain neutron stars, because that's basically what this is as well. This is a very unique type of a neutron star, or more specifically a pulsar, pulsating neutron star, that just so happens to be in just the right position and just the right orbit to suddenly start absorbing a lot of mass from its partner. With the one that was recently discovered being particularly interesting because it also seems to be way more massive than anything we've seen before, potentially even reaching the theoretical mass of what a neutron star can be. Anything more massive than that, and it might actually turn into a black hole, in the process initiating some kind of a very powerful explosion. But I guess let's start with the object itself. Where exactly is it, and what do we know about it? So all of this is from the study you can find in a description that essentially describes the object known as PSR J0952-0607, the fastest and heaviest known neutron star. This object is located in the Milky Way galaxy, but it seems to be a record holder for a lot of different things. First of all, it's about 2.35 times the mass of the Sun, making this object ridiculously massive compared to a lot of other neutron stars we've seen so far. On top of this, it spins really fast. So here's an example of a pulsar, a typical pulsar, that spins relatively fast, but not as fast as this one. Here the pulsations, as you can see, happen roughly around maybe 5 to 10 times every single second. But in this case, this is a millisecond pulsar, meaning that it actually spins at least several hundred times every single second. It's sort of difficult to imagine for our brain because it's just way too fast, but according to the recent observations, it has a spin of 707 times per second. So imagine this, but basically like 100 times faster. And because this object is also about 14 kilometers across, it makes it an extremely powerful entity. But by also being so massive, it has a lot of other features on the inside as well. And so in this case, thinking of this as basically some kind of a object made out of regular matter is somewhat incorrect because we don't actually understand what it's made out of. We call these objects neutron stars, but in reality only some of the outer shell is very likely made out of neutrons. The rest, and here we're talking about 500,000 masses of planet Earth, is essentially some kind of an unusual exotic object, very likely relying on quantum effects that we still don't understand. And this of course includes a lot of subatomic particles, a lot of up and down quarks, but possibly a lot of other stuff we cannot imagine. Things that scientists usually discover in experiments involving particle accelerators, but things that naturally seem to exist here at all times. And although today some scientists imagine this as a kind of a giant nucleus, something similar to what we find inside a typical atom, in reality the modern understanding of what's inside a neutron star is extremely limited. Here's one of the interpretations of what the scientists think might happen on the inside. So even though there are some neutrons and some electrons on the outside, the inside is mostly made out of Fermi liquid, basically a quantum effects liquid, but possibly some kind of a unusual exotic plasma representing the core. So in other words, when it comes to the mysteries of the universe, this is as mysterious as it gets. But the scientists behind the recent study decided to specifically focus on this particular pulsar, mostly because of its extreme components, and they wanted to discover its exact mass and why exactly it's spinning so fast. And they seem to have figured out a lot of these questions. First of all, they were able to directly measure the mass of this object. As I mentioned before, it's about 2.35 masses of the Sun, but could be actually even a little bit more massive. But they were also able to study some of the leftover plasma from the glowing companion, and also figure out what happened to this companion as this pulsar essentially ate it alive. Now, from a lot of previous observations, the scientists generally understand that in a typical black widow pulsar, which usually produce very powerful gamma ray and radio emissions, you'll have a lot of pulsations both from the pulsar and from the object around it. And this object will also be leaking a lot of the matter, producing a kind of a comet-like tail that's visible from really far away. Generally, it will look something like this, but if you were to actually look at it with a telescope, it will resemble this in very specific frequencies. And this has actually been seen several times. Now in this case, the cometary object itself is simply formed because of the motion of the star, or in this case the binary, and also because of the stripping of the material, as the neutron star doesn't just absorb some of the mass, but also illuminates it with its two polar streams, or these very powerful jets, coming from both directions. But what's particularly interesting here is that this process seems to actually then feed the star even more. So in other words, by basically just starting to illuminate an object somewhere out there, and this was by the way very likely some kind of a star at first, as all of this matter sort of gets disturbed and as all of it gets stripped away, some of it then creates an accretion disk around the neutron star and also ends up powering the neutron star even more, with the accretion disk and all of this matter also adding a little bit of angular momentum to the neutron star. Or in other words, the accretion disk gives the neutron star a little bit more spin, which then increases its rotation even more. And so even though initially it might have been spinning really slow or almost not at all, by doing this long enough and by creating more and more mass around itself, it sort of feeds itself even more, increasing its spin and producing even more powerful emissions in the process, with all of this becoming more and more rapid as the time goes on. And so this pulsar spin, once it starts, accelerates quite dramatically until eventually the star very likely either disappears or, more likely, turns into something much smaller. And in this case, the scientists believe that it created some kind of a planetary object around the system. In other words, right here, it's no longer absorbing a star, it's now absorbing the leftover planet, probably some kind of a gas giant, that used to be a star, but is now just a chunk of matter resembling Jupiter. And at some point it might even become smaller, possibly even resembling planet Earth. Although in this case, resembling is not really the right term. In terms of mass it might resemble a planet, but in physical terms it's basically this super hot object stretched into this unusual shape with a lot of emissions coming from certain directions. With this process very likely starting because the original star became old enough and started to expand, turning into what's known as a red giant. With this donor star, eventually, through the emissions and through the absorption of a lot of matter, basically disappearing completely, because now a lot of this mass was transferred into the neutron star, turning PSR J0952 into essentially the most massive neutron star found. But as I mentioned in the beginning, this might have also solved one of the mysteries we had about these millisecond pulsars. There have been several cases where these pulsars have been discovered completely alone by themselves, spinning very fast. And nobody could explain why they're doing so because that's not really how we believe they form. In this case, this might actually provide us with an explanation. Because as the neutron star in this case absorbs the star, it will eventually leave nothing behind, but will still be spinning pretty fast. With the planet either completely invisible or possibly even completely gone, the pulsar will then slowly start to slow down, but will still spin pretty fast for a pretty long period of time. Which of course implies that a lot of these millisecond pulsars discovered in the past are very likely just advanced versions of these black widow pulsars that we've discovered in a lot of different locations in the Milky Way. Which possibly finally solves their mystery and solves a lot of other mysteries about the neutron stars. But also explains why the term black widow in this case definitely applies to this particular object. They actually seem to be capable of completely destroying their partners. And not just destroying them, but absorbing their mass and literally eating them. And at the moment, this seems to be the best explanation for what we're observing from these different objects. I've always been kind of fascinated with the idea of magnets. Actually, ever since I was really young when I started to take apart some of my early toys and discovering magnets inside of them. And I think even today, magnets to me basically are like magic. They seem to have these really exotic properties and they seem to act in ways that you don't actually expect them to act, especially once the conditions become very extreme. And that's also why I always love talking about Magnetars, the most powerful and I guess the most exotic, most extreme and most fascinating magnets in the universe. Magnets so powerful that they tend to produce effects that we don't actually expect or can't even imagine, at least yet. And today we're going to be talking about a new record holder. Hello wonderful person, this is Anton, and today we're going to be discussing this relatively new study that was able to provide direct measurements and direct proof of the strongest magnetic field in the universe, the strongest magnet. Although here I have to clarify, this was the strongest detected so far, because theoretically the scientists believe something even stronger can easily exist somewhere out there. But in this case, this was a direct proof of such a field existing in a binary X-ray system known as J0243.6, a system that we believe contains two stars, a much larger donor star and a much smaller neutron star responsible for these very powerful emissions. And in this case, as the neutron star absorbs a lot of this mass, it also tends to produce very specific X-rays which can then be used to measure the magnetic field of the neutron star. And once in a while, as it goes through various outbursts, it becomes possible to measure a lot of things about the neutron star and its environment. Which is precisely what the scientists were able to achieve using a relatively new X-ray telescope that's actually run by the Chinese agency. It's actually known as the InSight HXMT and is the China's first X-ray astronomy satellite, as it says in the title right there. Although I shouldn't have probably mentioned that because every time I make a video and I mention China to some extent, the video instantly gets a lot of dislikes. But that's expected because of our biases. Anyway, moving on, let's discuss the science. So, as you probably know by now, neutron stars and specifically magnetars theoretically represent the most powerful magnets the universe can produce. Even the most powerful black hole out there cannot actually match a typical neutron star. And the theory and the math behind all of this is pretty solid. As a matter of fact, the scientists have various concepts defining how much magnetism a typical neutron star can produce, and also how it's actually able to create all of these very powerful magnetic effects. So for example, some of the magnetic field is produced because the neutron stars spin so extremely fast. They can actually spin several hundred times every single second. While on top of this, they also have a lot of the plasma circulating around them, the plasma that's basically coming from the donor star. This plasma also creates a very powerful magnetic field as well. Altogether, this creates effects that are kind of difficult to imagine because sometimes they actually start to act against the gravity. And very often these effects become so strong that they actually polarize the space itself around the neutron star. Now it's actually sort of difficult to imagine, but the space itself, the empty space around the neutron star, becomes very different. It actually starts to produce particles, it also starts to create things that would be otherwise impossible, and even acquires mass from nothing, which then also results in what's known as the dilation effect. So very powerful magnetic fields actually end up creating some really exotic effects. And super powerful magnetic fields even start to act in ways that are difficult to describe mathematically. As a matter of fact, the linear representation of the magnetic field that works on planet Earth becomes sort of impossible. There's something known as the Schwinger limit, where essentially the magnetic formula kind of breaks down, and various particles start to act in very strange ways. At these magnetic strengths, any particle inside of this field can be easily accelerated to the same speeds as what we usually have inside particle accelerators in just a minute volume, something that's only a few micrometers in size. So basically here things just don't really make sense anymore. And obviously if you were to find yourself in one of these fields, yeah, that would not be very pleasant. Not only would you instantly disintegrate, but all of your matter would then accelerate to ridiculous speeds and would very likely become energy, while slowly being absorbed by the Magnetar. Although that's actually a very interesting topic to cover in one of the Halloween videos. Maybe we'll talk about this in the future. But anyway, this limit usually occurs at around 4 billion Tesla, or around 40 trillion Gauss. We're going to be using Gauss in this case because it's a much more common unit used in science. And even the simplest neutron star will normally contain approximately a trillion to possibly 10 trillion Gauss of magnetic energy. In other words, the majority of them already almost reach that limit, even if they're not Magnetars. But pretty much all of the known Magnetars to us, in theory, have a much stronger magnetic field. Possibly even 100 times as strong as the Schwinger limit. Here we're talking about 1000 trillion or a quadrillion Gauss, with the upper theoretical limit being approximately 100 quadrillion. At this point, even for Magnetars, the theory starts to kind of break down. Now there could be more powerful Magnetars, but nobody really knows, and the math doesn't really work after that. But all of this is of course theory. It's kind of difficult to try to test this or to measure the field, because we obviously don't have any way to, for example, bring a couple of wires there and then try to measure the levels of electricity in order to measure magnetism. And so the only way to measure the magnetic field on various objects out there is to try to observe what's known as the cyclotron absorption lines in various X-ray emissions. Or basically, if you have the X-rays coming from this region and you suddenly find these absorption lines at certain frequencies, it indicates that something interacted with the X-rays, and in this case, depending on the frequency, it becomes possible to determine the actual power of interaction. And so that's kind of what the scientists discovered coming from the system. By looking at this particular neutron star binary, the scientists found the absorption line at approximately 146 kV, which implies that as the plasma in the accretion disk falls into the magnetic lines, the X-ray radiation that's released creating various jets then has something absorbing it with that very specific power. All of this is believed to be caused by a kind of a resonance wave that's created around the neutron star with the electrons forming certain frequencies. And by using the theory behind this, it becomes possible to then measure the magnetic field that generates these resonant waves created from the electrons. And because in this case this is also known as the ultra-luminous or very bright X-ray pulsar, the luminosity of the X-rays here allows the scientists to see things that would be otherwise impossible. And so it looks like in 2017, during such an outburst, the magnetic field around this pulsar increased to approximately 1.6 billion Tesla, or about 16 trillion Gauss. So approximately 1/3 of that limit I previously mentioned, and much smaller than what we expect from a magnetar, but more powerful than around a typical neutron star, which also beats the previous record from another pulsar established in 2020. That pulsar had the strength of about 1 billion Tesla. But these numbers are so huge that it becomes almost impossible to imagine the strength of these fields. And actually visualizing this is almost impossible. But just to give you a comparison to some of the objects around us, well, right now, by being on the surface of planet Earth, you're experiencing approximately half a Gauss. Once again, this is 16 trillion Gauss, so approximately 32 trillion times higher. Here's a rough visualization of what 1 trillion looks like, with a million being this tiny dot right here, but we're talking about 32 trillion, stronger than planet Earth. Now in comparison, a typical fridge magnet is about 50 Gauss, or about 100 times stronger than the surface of the planet, but we're talking about 32 trillion. A sunspot would have the strength of about 1500 Gauss, whereas the equator of Jupiter has the strength of about 4000 Gauss, 8000 times stronger than the surface of planet Earth, but not 32 trillion, with the MRI machines usually having the strength between 3000 to approximately 70,000 Gauss at their strongest, with this neutron star still being 228 million times stronger, roughly, than the strongest MRI machine on the planet. With all of this being officially confirmed using the X-ray observations from this particular binary system. In this case, also discovering that neutron stars do seem to have complex structures, magnetic structures, with the actual dipole moments very likely being different from your typical magnet. Or in other words, the magnetic field structure around a neutron star is much more complex and seems to involve various features that we still don't really understand very well. The dipole field in this case is not symmetric like in a traditional magnet, with the magnetic structure resembling something we can't imagine. All this may be due to the fast rotation of the pulsar, or possibly due to some other theory we still don't really understand. But all of this means that there are going to be so many new discoveries with all of these new X-ray telescopes in the coming years. Back in the early 70s, the scientists were really surprised to discover this blinking light you see on the screen. This was the first ever pulsar we've discovered, the Vela pulsar. The extremely powerful object, a neutron star, that seems to generate these very strange pulsations every 1.3 seconds, something that back then was very difficult to explain until the scientists realized that neutron stars were real and that they were actually producing these very strange signals pretty much everywhere around the universe. But with time, as our technology advanced, the scientists have started to discover even more unusual pulsars with more unusual features that are even difficult to explain today. And so when it comes to pulsars and neutron stars, there is really no limit to various mysteries in regards to their signals. But because they're so predictable and seem to produce these signals at extremely specific intervals, they're also an extremely important part of us trying to understand everything in the universe. And so today we're going to be talking about this new discovery, another unusual neutron star or pulsar that we've never seen before, that seems to push the boundaries even more. Hello wonderful person, this is Anton. So let's discuss exactly what the scientists discovered recently and why this particular pulsar seems to have surprised them so much, with the signal coming from this pulsar visible in this video provided by the University of Sydney. And by observing this, you can maybe even notice that something seems to be really strange. First of all, it pulsates extremely quickly, but also it seems to pulsate with a somewhat different profile compared to other pulsars in the galaxy. But not different enough to be some kind of a new phenomenon, yet similar enough to other neutron stars and pulsars that it's very likely just some kind of an evolved state. And here it's also important to understand that when it comes to various pulsars we've discovered so far, there's already quite a diversity. As a matter of fact, not all pulsars can be created by neutron stars. There's at least one white dwarf known to produce very similar signals, with signals in this case taking approximately 2 minutes between them. This is a system we've discussed in one of the previous videos, and it's known as AR Scorpii. But this time, the scientists who are actually studying Vela X1 binary, a binary that's known to produce a lot of X-rays, using the Meerkat telescope in South Africa, accidentally discovered an unusual pulse that lasted for approximately 0.3 seconds, or 300 milliseconds. With the flash itself being somewhat similar to what we expect from a neutron star, but not really repeating as much, and more importantly, still possessing very different characteristics of a typical pulsar or even a magnetar. And so the scientists decided to go through the data collected over several years to see if they can actually find other pulsars coming from this region, and to actually discover what's happening here. And they actually did find quite a lot. The pulses that were previously missed by the automatic detection system. Mostly because the system never really looks for these very long pulses, something that's longer than 20 to 30 milliseconds. And moreover, by analyzing the signals, they discovered that they were actually repeating extremely accurately, with the period being approximately 76 seconds. And 76 seconds is a really long time for a pulsar. The previous record holder was actually 23 seconds, and even that was very difficult to explain. Pretty much every other pulsar we know usually has a repetition of just a few seconds or possibly even milliseconds. They never really have these long periods. And so something really unusual was happening around this object. And just like some of the other unusual pulsars we've discovered in the last couple of years, it also seemed to possess features of both Magnetar and a pulsar. And specifically, it seemed to produce 7 distinctly different pulse shapes, with certain pulses representing what's known as a quasi-pulse, with the signals possessing what's known as polarization, suggesting that this is coming from a very highly magnetized object, and certain signals possessing what's known as a quasi-period, which suggests that there is some kind of an oscillation or some kind of a periodic activity happening around this object. It could be because something is orbiting around it, or it could be because something is disturbing it very regularly. And so because of this diversity in different pulses, and because of the intensity of the pulses, currently the scientists cannot really explain what's going on here. And they obviously cannot explain why this object is pulsating every 76 seconds and not just a few seconds like a typical pulsar. And interestingly enough, the pulsations here seem to be very accurate. They were even able to predict the next pulsation down to approximately 100 millionth of a second. And so the discovery of this unusual object challenges a lot of things we know about pulsars and potentially presents a completely new phenomenon. It's even been detected in a region where we don't really expect any neutron stars that are still active. There could be some neutron stars that are silent and have long stopped producing signals a long time ago, but discovering a neutron star that produces radio signals was never expected from this region. Mostly because a lot of stars in this region are actually pretty old, and the activity in this region has long stopped producing anything. And more intriguingly, the signal itself also to some extent resembles fast radio bursts, the other mystery we still have trouble solving. But in this case, it's slightly longer than a typical fast radio burst, and also doesn't seem to possess as much energy, suggesting that maybe this object is sort of like what happens to fast radio bursts, or the sources that produce FRBs, once they kind of reach the end of their lifetime. And all of this could be related to what we usually refer to as an ultra-long period magnetar, a super powerful but still somewhat hypothetical object that could be responsible for most of the mysteries we're observing. Either way though, this could be the first member of this new class, the ultra-long period neutron star with magnetic properties, which could be the next step in the evolution of ultra-long period magnetars that we think it might be responsible for FRBs. So basically that's sort of like where they end up afterwards. They slowly produce less and less energy, and they slowly become less magnetic. But there's still quite a lot of unanswered questions even here. First of all, we obviously have no idea how many of these objects exist in our galaxy. Right now this is the first one. Second of all, it's unclear how long this object has been active, and how long it's going to stay active, or how it's going to change over time. The scientists behind the paper do suggest that it's about 5.3 million years old, but how long it's going to remain active is still unclear. At the same time, because of the inclination toward us, this object is actually only visible about 0.5% of its rotational period. So even the fact that the scientists were able to find this pulse is extremely lucky. Further observations though are going to be kind of difficult. And that's basically because the jets coming from this object are not really directly pointed toward us. They're pointed toward us with a slight inclination. Nevertheless, it's still a pretty exciting discovery because it could actually connect a lot of these different mysteries we observed in the past few years. For all we know, that's exactly how fast radio bursts are produced to begin with, except that in this case this is sort of the long-term evolution of this object, and it could also represent a natural progression for a lot of different pulsars or a lot of different magnetars. And so for all we know, this is just the beginning of the story and the beginning of these exciting explanations that could help us understand the universe better. But when it comes to pulsars, they also have a lot of practical use. As a matter of fact, today they're used in a lot of different fields, including fields involving gravitational detectors, fields involving the very precise measurements of space-time disturbance, or essentially fields involving any kind of a precision mapping. As a matter of fact, you might already know that the iconic Voyager probes inside of them contain these two golden records. And these two records contain what's known as a pulsar map, the map to the solar system based on the observations of different pulsars. And that's because pulsars produce extremely accurate navigation maps and also produce extremely accurate clocks, something that the scientists are trying to explore here on Earth for any future use in regards to navigation around the solar system or even for things like GPS. That's because pulsar clocks are even more accurate than a typical atomic clock. And so if we do start using pulsars for a lot of different things on planet Earth, for navigation, for communication, for measuring time, understanding how they evolve and trying to understand what happens inside of them is actually really important, because if suddenly a pulsar changes its pulsations and we can't explain why it did so, it might create certain problems for a lot of different technology on the planet. But that's of course something we don't really use actively yet, even though we use something else from outer space that's just as exciting. The vast majority of extremely accurate mapping on the planet is actually done using quasars. We don't use stars anymore, we don't really use anything else, but we do use very precise locations of quasars around the night skies in order to determine where things are on our own planet. When it comes to mysteries of the universe or explaining how the universe works, neutron stars have always been at the forefront, specifically both at providing new mysteries and at helping us resolve some of the unusual observations from across the universe. For example, how several elements such as gold and platinum can be created through collision of neutron stars. Or how certain mysterious emissions such as the iconic fast radio bursts could possibly be produced through a very unusual interaction of a neutron star with something in its surrounding. And so because of this, a lot of different theoretical physicists usually focus on neutron stars and the math behind them in order to help us understand everything around us. Hello wonderful person, this is Anton, and so today we're going to talk about several different studies that potentially help us explain a few different mysteries, including fast radio bursts, and also help us understand what happens to certain neutron stars in certain conditions when they end up colliding with one another and instead of producing a black hole can actually create something a little bit different. The object the scientists refer to as a magnetically supermassive neutron star. An object that could only exist for maybe a few years, but could potentially create a lot of different signals we're observing around the universe but cannot currently explain. And so how exactly does this work and what exactly do the scientists propose here? Well, first of all, we know that a typical neutron star, a lone neutron star, is usually produced during some kind of a supernova of a star that's not really massive enough to produce a black hole, but is more massive than a star that would usually end up as a white dwarf. In this case, when it's a binary system and there are two massive stars, in some cases, this can actually result in two different neutron stars in orbit around one another. But in some cases, these two neutron stars can actually end up really close to one another and start interacting and at some point collide. And this event has been officially confirmed a few years ago through the detection of gravitational waves coming from two objects that were not massive enough to be black holes, but were more massive than what you would call a white dwarf, with the objects very likely producing some kind of a black hole as a result, and at least one event also resulting in what's known as a hypernova, an extremely bright event visible from a very far away distance. Back then, this was also a confirmation that a lot of gold and a lot of elements like platinum are also produced during these very powerful collisions. And today it's believed that most of the gold, if not all of the gold, is actually produced this way. But it was also believed that these types of collisions will normally result in the production of a black hole, and this black hole is most likely going to be almost completely invisible. With all of this relying on a very interesting concept known as Tolman-Oppenheimer-Volkoff limit. The limit of the mass of a typical neutron star. Now, interestingly enough, it's not really that well known. As a matter of fact, the math behind it is pretty complex. And so unlike the Chenery-Zucker limit for white dwarfs, which states that once a typical white dwarf reaches the mass of about 1.3 masses of the Sun, it's going to go supernova, for neutron stars, this mass is very roughly defined, anywhere between 2.2 and 2.9 masses of the Sun. And it would also only apply to neutron stars that are not spinning, and most neutron stars spin ridiculously fast. And for a spinning neutron star, this limit can increase by up to about 20%. And so even today this particular limit and its value is not really known. But one of the previously detected neutron star collisions, such as the one you see right here known as GW170817, detected in 2017, suggested that this limit is about 2.3 masses of the Sun, with the original star being anywhere from 15 to 20 solar masses, suggesting that if a neutron star reaches the mass of 2.4, 2.5 and so on masses of the Sun, it then goes supernova, producing a small, very highly charged black hole in its place. But even here there are quite a lot of discrepancies and quite a lot of mysteries based on the observations of neutron stars from around our own galaxy. For example, in the past several neutron stars have already been identified and confirmed, but at the moment nothing with the mass of over 2.8 masses of the Sun. The record holder right now seems to be this pulsar you see right here, located in a globular cluster. Its mass is about 2.7 masses of the Sun. Then on the opposite side of the spectrum we have the smallest black hole detected. In this case it's also from gravitational wave detections back in 2019, and it's a black hole known as GW190425. The total mass of this black hole is approximately 3.3 masses of the Sun. And in between that we have some very unique and somewhat exotic objects such as the famous SS433. This is a binary system that's pretty well known to scientists, but nobody is entirely sure what exactly it is. It could be a black hole, it could be a neutron star, or it could be some other exotic object. It's known as the most exotic star in the galaxy, and it also is an object that produces a lot of anomalies. An older video on the channel, somewhere right there or in the description, explains a little bit more about this particular object. And the mass here could be up to about 3 masses of the Sun, so it's basically somewhere in between the smallest black hole and the biggest neutron star. And so it's kind of been previously suggested that it could be some kind of a neutron star that's just spinning extremely fast, because it's believed that if a neutron star spins really fast, almost at its limit, the rotation itself can prevent it from collapsing into a black hole until the spin slows down. Or in other words, the centrifugal acceleration in this case prevents the gravity from basically collapsing in the neutron star and creating a black hole. But the scientists behind this study proposed something entirely different, and they proposed something that could maybe explain several observations and several mysteries in regards to various magnetic neutron stars. They suggest that a neutron star does not have to spin very fast in order to stay stable for at least a few years, and it might even not collapse into a black hole and be really massive, more massive than its limit would allow, if instead of a spin it possessed an extremely powerful magnetic field, such as what you would expect from a typical magnetar. And so in this case, if a collision between two neutron stars ends up creating a single object with a very powerful magnetic field, it can actually stay as a neutron star for at least a few years, with the magnetic field in this case providing the support preventing the neutron star from collapsing further. And in this case, this unusual magnetic neutron star with time will start losing its energy. And because of the diffusion of energy from its poles, it's slowly going to transform from releasing gamma rays and X-rays to releasing low power energy, including of course radio waves. And when the energy is no longer released, that's when it goes supernova and collapses into a black hole. And more importantly, if such a star existed, they also provide several different ways we could potentially find these stars, because they would actually produce very specific types of emissions, and what's interesting is that one of their predictions kind of suggests that these emissions would be similar to what we usually refer to as FRBs, fast radio bursts. The bursts that represent one of the bigger mysteries in modern astronomy and that are usually associated with very highly magnetic objects, with at least one burst coming from our own galaxy, already corresponding to a very well-known magnetar that is also known to produce X-ray bursts. And so could this really be how FRBs are produced? But in their paper they go through a little bit more detail, suggesting that other signals should be detectable as well if these objects truly exist. For example, there should also be very unique signatures consisting of quick gamma ray bursts and quick X-ray bursts, at least during the initial stages of the existence of these neutron stars right after their collision, with all of these powerful emissions eventually changing into radio emissions as the gravity field of the neutron star takes over and as it starts to sort of fade and slowly turn into a black hole, with the final collapse also releasing some type of energy as well. But currently, there's really no evidence for such fast gamma ray bursts or X-ray bursts, so we don't really know if these objects truly exist, and if any of the fast radio bursts are produced by these exotic neutron stars. And even though technically it could be detected using modern technology, the gamma ray telescopes and the X-ray telescopes are not nearly as advanced as some of the radio telescopes on the planet, so it's a little bit easier for the scientists to find fast radio bursts compared to some kind of a fast gamma ray burst that would require a completely new type of observation. But if this paper is correct, it means that certain fast radio bursts are eventually going to disappear and potentially even produce some kind of a supernova-like explosion, which should be visible with modern telescopes. And since these objects are expected to exist for only a few years, it should be happening in our lifetimes. If this doesn't happen, it means that FRBs are maybe created by something entirely different. Nevertheless, a pretty exotic and pretty interesting proposition for a type of a neutron star that could maybe explain different mysteries in the universe. But when it comes to FRBs, there are so many different explanations, with many actually making sense. For example, one of the most recent propositions was in regards to FRBs potentially being planets in orbit of, once again, a neutron star. And so at least one paper proposes that if a neutron star has a planet, and we of course know planets do exist around neutron stars, with the recent video that you can find right there or in the description explaining this in more detail, if planets have an orbit that's not circular, and if they do actually come relatively close to the neutron star, they might go through a typical tidal disruption process when an object starts to fall apart next to a very dense, very massive object such as a black hole and a neutron star. And as this planet starts to lose some of its mass, and starts to become tidally disrupted by this object, some of the material from the planet might end up crashing onto the pulsar itself, onto the neutron star. With this material then creating the observations we see, as some of these clumps, as they interact with the neutron star, produce various types of emissions because of the ridiculously powerful collisions. And if some of these clumps pass through what's known as the stellar wind, or through some of the magnetically charged particles produced by this neutron star, they'll actually start releasing very powerful radio waves as a result. So this is maybe one other way FRBs or various radio emissions from neutron stars could be produced as well. And in this case, by running calculations of famous fast radio bursts that do repeat, the scientists discovered that it also makes sense if it was just a planet creating this. So once again, another potential explanation, but nothing definitive just yet. But as I mentioned in the beginning, neutron stars seem to be the source and the potential solution to many different mysteries of the universe. Mysteries that in time we're hoping to be able to answer through thorough observations and various studies involving various neutron stars we've already discovered. Hello wonderful person, this is Anton, and today we're going to be discussing some of the new discoveries and some of the new analysis in regards to various pulsars and the mysteries of these somewhat strange objects, with a couple of papers exploring slightly different things. For example, one of the papers tried to figure out if pulsars and their unusual tails that some of them produce can actually explain why there is slightly more antimatter present in our galaxy. Whereas some of the other papers focusing on the idea of planets around pulsars. They wanted to discover what is the likelihood of finding more planets around these objects by looking at approximately 800 various pulsars in our galaxy and trying to find out if any of them were hosting any planets. And so let's discuss these discoveries and these studies in a little bit more detail. And I guess let's start right here with this beautiful image and this beautiful video created by the scientists from the Chandra X-ray Observatory. The image representing a pulsar known as PSR J2030 plus 4415. Unlike some of the other pulsars in our galaxy, this one is unusual because it's actually moving through our galaxy really fast. Its overall velocity is approximately 450 km per second. And it's probably doing so because the supernova that created this particular pulsar or some other very cataclysmic event very likely kicked it out from its original system and gave it this velocity that it currently has. But unlike some of the other pulsars, it also seems to have a comet-like tail of particles extending as far as 7 light years away from the object in the center. With particles in this case very likely being matter or electrons, but also antimatter or positrons, which the scientists believe might actually help us solve the mystery of the Milky Way, where for some reason we do tend to find a little bit more positrons than we expect theoretically. And so scientists behind this paper do think that maybe some of the pulsars that are moving in a very similar fashion could be responsible for the production of this extra antimatter. But this particular pulsar possesses some other features we've never seen anywhere else before. Now obviously there's this long tail that you see that extends to several light years, but there's also this smaller tail that you see coming from the pulsar that most likely formed approximately 2 or 3 decades ago, when in this case the scientists believe the pulsar might have actually caught up with the shock wave or the bull shock that was in front of the moving pulsar that might have slowed down for one reason or another, with the star sort of punching through the entire bull shock, producing the effects, which suddenly led to a lot of different particles being leaked from this region and being accelerated along the magnetic field lines, making all of this move at ridiculously high speeds, probably about a third of the speed of light, which then also produced all of these X-ray observations we're seeing with Chandra right now. So all of this is to some extent a relatively recent observation, and we've just never really seen anything like this before. In this case, potentially helping us solve a lot of mysteries of the galaxy and possibly even discovering new mysteries we didn't know existed. But some other scientists wanted to actually see if we can find something around all of the known pulsars to us, and specifically find out how likely is it that some of these objects can actually have planets around them. Now it might sound kind of weird, but remember, the first ever planet ever discovered, and actually the first 3 planets, were all around a pulsar system, the system we sometimes refer to as LICH, with the scientific name of PSR B1257 plus 12. With the 3 unusual planets discovered back in 1992 and 1994 being essentially some of the strangest planets we've discovered to date. One of them is still the smallest or the least massive planet we've ever found. This planet right here is only about 50% higher in mass than our own moon. The planet that we sometimes refer to as Droger or PSR B1257b. All of this located approximately 2300 light years away from planet Earth. And this was of course discovered using a technique known as the Pulsar timing array, which in essence work really simply. By looking at the pulsations coming from a typical pulsar, and by timing these pulsations extremely accurately, if we ever see any deviation from these pulsations, and especially if these deviations are somewhat cyclical or have some kind of a period, it suggests that something could be orbiting around the pulsar and causing it to shift back and forth just a little bit. And if these pulsations are extremely minuscule, it can only mean that there's probably a planet around the pulsar. But in this case we have to be a little bit more careful and look at some of the nearby pulsars as well, because if they all tend to have very similar observations and very similar periodic oscillations, it can only suggest that they're probably being affected by very large gravitational waves, maybe even from supermassive black holes. And so that's kind of the idea behind the study you can find in a description that looked through the data of 800 different pulsars known to us, specifically looking for these minute variations in the pulsation of these neutron stars. And remember, these objects are super accurate. As a matter of fact, there have been several studies suggesting that we can use pulsars as something to replace the atomic clocks on the planet. That's how extremely accurate these pulsations are. And that's of course the main reason why such a tiny planet was even discovered around the pulsar system back in 1994. Even to date, we haven't found anything smaller or less massive than this particular object, and in reality our telescopes are just not powerful enough to see these types of planets either using transit method or using any other method used to detect planets. But ever since the original detection of these planets in 1992-1994, there were always these unanswered questions. First of all, is this just a really lucky find? Are these just extremely super rare? But also, how exactly did they form? What created these planets and how can they possibly exist around a neutron star, around a pulsar? Well, in order to answer the question of their origin, there have been several propositions. One of the propositions involved a potential capture during a collision between 2 objects that form a neutron star that ends up being a pulsar. So in this case, if one of these objects already had some kind of a planet and it ends up being captured by the final product, it sort of stays in orbit and most likely will remain there for a pretty long time. Although in this case, because of the extreme conditions and lots of radiation, a lot of these planets will probably undergo some major changes and possibly even potentially disappear completely. For example, a very common system that's known to us, that is very easily visible as well, is something referred to as a black widow star, or sometimes known as the redback star. These are pulsars that are so close to the object near them, very often some kind of a gas giant or some kind of a planet, that the radiation around them starts to literally evaporate the object that's in their orbit, producing a huge amount of particles around the system, and resulting in a very long, very powerful bull shock that's visible from far away and that also propagates throughout the galaxy. But in some cases, it's also believed that maybe some planets could be formed after the supernova creates the neutron star. In this case, the material that doesn't end up moving too far away from the neutron star has a chance to potentially come back and create some kind of a protoplanetary disk around the neutron star, which eventually starts reforming into planets. In other words, theoretically, we could have new planets forming from the old material that used to be a supernova. And this could end up producing planets that have relatively simple and relatively stable orbits. But naturally, we've never really seen any proof of this, and we don't really know if that's actually possible. And the third way that some neutron stars and some pulsars can potentially create planets is once again through that system of black widow stars. In some cases, one of these neutron stars is a lot more powerful than the other and might actually produce way more radiation. Or it could also cause some kind of a disruption through various approaches with a slightly smaller neutron star. Either way though, whatever the partner was, the larger neutron star can actually cause its partner to completely evaporate, leaving behind nothing but a core, with the core itself potentially being quite exotic. Some papers suggested that it's some kind of a really large crystal, some other papers even called this possibly some kind of a diamond. Either way though, whatever it is, it's definitely exotic and definitely nothing we've ever seen before. But these are just 3 suggestions for how some planets can form around pulsars. And so, going back to that paper from just a few weeks ago, did they find any more planets around these 800 something pulsars? Well, in short, the answer seems to be not really. In this case, the vast majority of the pulsars you've taken a look at seem to not possess any planets that are 2 to maybe 8 masses of the planet Earth. And though in theory smaller planets and less massive planets could exist here, there was no evidence of any of these planets around any of these 800 objects. And even though 15 of the 800 objects did possess some potential irregularities and seemed to have some periodicity coming from something, in this case it was just not enough to prove that any of these were actual planets. As a matter of fact, the more likely explanation here is in regards to very powerful magnetic fields present around a typical pulsar. In this case, the magnetic field is sometimes so strong that it does have a tendency to shift some of the pulsations slightly depending on the interaction of the particles nearby. So unless this is something that happens for a long period of time and is visible through many different studies, it's normally just a temporary event. And so in this case, this is exactly how the scientists in this paper explain some of these observations. But of all of the 800 pulsars, one was the most likely candidate to potentially possess a planet. The pulsar known as J2007+3120, with the oscillations present around this pulsar suggesting that something was orbiting around it every 723 days. But this is still very preliminary and could still have some other explanation that could also not be a planet. Either way, 1 out of 800, and that suggests that, well, obviously, pulsar planets seem to be extremely rare, and the original detection from 1992-1994 was just a fluke. We really got super lucky. Which kind of makes sense, because once again, these neutron stars and these pulsars create some of the most extreme environments where it's extremely difficult for any type of matter to survive, with most things, including other stars and other planets, simply evaporating over time. And so the fact that this strange pulsar system even exists and seems to possess 3 different planets is already kind of difficult to explain, and is not something we actually have any explanation for right now. Although I guess by studying this particular system in more detail, the scientists might be able to come to some conclusions and some possible answers after a few years. On that note, well, these are really exciting discoveries and might actually help us understand a little bit more about our galaxy and of course our place in the universe as well. Until we learn more about pulsars or some other neutron stars, that's all I wanted to mention. Thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, and maybe come back tomorrow to learn something else. Maybe support this channel on Patreon by joining channel membership or by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.